Okay. I have it here.
So,
Professor Mohammed
mas
Zia.
ponham a mostrar ali a... Não, mas ponham para ali. Espera lá. É assim. Espera lá. Mas a ideia era... Não, não.
Yeah, here. I have this thing.
Sorry.
I have this information.
Yes, I sent you so that you could...
I opened it. So I read this. Like he needs to be online.
Se calhar o senhor vai ser. You gonna sit there? Yes.
Miguel, como é que pões isto para lá? Não está a dar.
Ok.
Virar a apontar para a mesa presidencial. Ok.
Well, that's better.
Pronto. A questão é que isto aqui não está a deixar... já está. Ok. Good morning, Zia.
Good morning, how are you doing?
I'm fine. Something went wrong in this.
Não é preciso fazermos nós a partilha, o senhor faz ele a partilha,
Ok.
só experimentarmos, está bem?
Sim, ok.
Shall I go ahead?
Está mais alguém aqui? Não, está.
Only two of them. So both of them here.
It's all... but there's Zia here.
The same guy. Same person. Same person doing both.
Okay.
Yeah.
So,
Yeah.
Yes. Good morning, Dr. Mohammed Zia Alavi. I hope you remember me. Krishna Bilikiri.
There and speak
He-
there.
he's here.
Yeah, we'll see you. You sit there.
Definitely, I remember you. You're Krishna, am I right? How are you doing, Krishna?
Yes, fine. Thank you. How are you, Mohammed?
Good, very good. Good to see you.
Good to see you.
I wish I was there. Yeah.
Yeah. Okay, so we have Dr. Alavi here with two presentations online. Please go ahead and introduce yourself, but I'll just read the two titles of your presentation. How does high RAP content affect the performance, properties, and durability of rubberized asphalt mixtures? This is one. And then the other is sustainability and performance evaluation of rubberized asphalt mixtures using different production methods. So you have 30 minutes in total for both presentations. So please go ahead and start. Thank you.
Sounds good. Sounds good. Thank you very much. So you can see my presentation, am I right? Just to make sure that
Yes, please go ahead.
I make the screen. So, first of all, I'm really happy that I have this opportunity to present the work that we did at the University of Tehran here. I was there actually, but because of the current situation, I couldn't be able to actually travel over there. So, as you mentioned, doesn't have content affected the performance properties and durability of rubberized asphalt mixtures. So this work actually done by my one of the former PhD, former master student, Mr. Mohammad Akhlawi, and one of the current MSc master students, Mr. Mohsen Amjadi. So let's start with that. So the outline of the presentation, as I said, so it's first introduction, objective, research scope, experimental plan, result and discussion, and finalizing the presentation with the conclusion about the current study. So as you may know, all of you know that we all here, all advocates of asphalt rubber binders and rubberized mixtures. So using the asphalt rubber binder have several benefits, including the recycling the material, reducing carbon footprints, improving noise reduction, and enhancing durability and longevity. Yesterday, Dr. Kalush mentioned that we all know, we all passed the stage that we mentioned that asphalt rubber binder and rubberized mixers are great, and they have basically approved performance from different test methods and also the field evaluation. But here, what we want to mention that what's happening that if we add reclaimed asphalt pavement to these rubberized mixtures. For wrap material, we also know that it has several benefits, including reducing the cost of the project, lowering emission for about 35% equivalent CO2, and at the same time, we maintain the performance of the basically asphalt material. So the problem is that we don't know really what's happening when we add wrap to the rubberized mixtures. We know that there are some issues with wrap usage in the asphalt mixtures, including that because of the aged asphalt binder in the wrap, so the fragility of the mix increases, and we may have these mixes may be more prone to cracking at cold temperature or under heavy repetitive traffics. So because of that, at the high wrap content, we usually use rejuvenators, as we all know about that. And there is a trade-off in the performance of the wrap mixtures. We know that when we add wrap to the mixes, then we make the mixes stiffer and the resilient modules increase. So therefore, in terms of the pavement design, we may be able to make the thinner pavements at the same time. It's improved rotting performance, but on the other hand, we have a problem with cracking. So this is what we want to see in the rubberized mixes as well. For this reason, so we consider four main objectives for this study. One is to evaluate the moisture susceptibility of rubberized mixtures with high wrap content. The second one is to see how the high content of wrap in the rubberized mix affected the cracking performance and fatigue performance. Third one is to see if rejuvenators work in these type of mixtures as well. And the last one is to see the rotting resistance of rubberized mixes containing high amount of wrap. So the research plan followed this flowchart, basically choosing the material, selecting the optimal dosage of rejuvenator for the material, then preparing the asphalt rubber binder using wet process, and then making a control mix by using a base binder, a control mix with rubberized binder, and also rubberized mixes containing 30-50% wrap. And then evaluating the properties, as I mentioned, TSR test for moisture susceptibility. And for the cracking performance at the intermediate temperature, we use SCB IP test method. For the rotting performance, we use dynamic creep test. And we also basically did some tests using 4-point bending beam with 800 microstrain, a high level of microstrain, basically. To see how the properties of this material may affect by incorporation of wrap. For the asphalt rubber binder, we use base binder 8500 penetration grade binder, which is a common type of a binder used in Iran, especially for the modified, as a base binder for modified binders, polymer modified or rubberized binder, or asphalt rubber binder, as I mentioned. Using the wet process, we add 20% asphalt rubber, we add 20% chrome rubber to the base binder. We mix those at 170 degrees C for 60 minutes using a mixer with 3000 to what is usually used in Arizona or California, but it's more close to what is used in Florida. So it's a fine rubber compared to the one that's used in the states that I mentioned, that they usually use rubbers passing number seat number 8. So because of that, we are able to use this asphalt rubber binder because of the fine rubber particle in dense graded mixes. So our mix are dense graded in this study. The aggregate type of the mixtures are limestone aggregate with a nominal maximum aggregate size of 9.5 millimeter. And basically for the one without wrap, there is no rejuvenator needed. For 30% wrap, again, we found that there is no rejuvenator needed for that. We find the dosage of rejuvenator by checking the softening point of the age binder in the wrap. and to see how much regenerator we can add to basically restore the properties to the original binder in terms of the softening point. So for this reason, at the 50% wrap, we use 4% rejuvenator, and at the 70% wrap, we use 9% rejuvenator. The type of rejuvenator that we used in this study is basically a commercial product produced in Iran. Is I can say is more or less is like a very soft binder with a very low amount of asphaltene in it. More or less is like a molten phase of the asphalt binder, and they also incorporated a few amount of I can say nanoscale polymer to this material to make a rejuvenator as a polymer modified rejuvenator. So the test that we performed is moisture susceptibility according to the H2T 283 at 25 degrees C measuring ITS values, then semicircular bending test following the IFIT specification at 25 degrees C to see the cracking performance. For the beam fatigue test, we follow the H2T 231 at 20 degrees C at 800 microstrain, and the dynamic creep test following the NCHRP 9-19 specification, and we run the test at 54.4 degrees C. You can see the shape of the basically instruments here that we run the test. So if I want to actually explain what's happening to the material from each of the tests is as this. So as you can see for the indirect tensile strain in wet and dry condition, asphalt rubber has a better performance compared to the control mix with 8500 stretching gauge binder. A bit better performance, but when we add a wrap to the mixtures, the indirect tensile strength increased very well. So, and the thing is that at 50 and 70% wrap, the indirect tensile strengths of the mixes are relatively similar to each other. We can explain that more or less because of the effect of rejuvenator. So when we add a rejuvenator to these two mixes, basically these two mixes behave similarly because the gradation are the same, the binder content is the same, only the properties of the binder may be different, but when we add a rejuvenator, we believe that we restore the properties of the age binder. So regardless of the amount of wrap, basically we found that the ITS values are similar at high amount of wrap. And as you see here, the moisture affected slightly on the ITS values. We can see that more clearly here that what's happening with the TSR. All the TSR values for the mixtures are above 90. For the wrap incorporated mixtures, the TSR values increased, and it shows that better durability against moisture damage. We see a slight reduction in the TSR values using the asphalt rubber without wrap, and it might be because of the because we didn't change the amount of binder in these mixtures. All the same binder contents. They are all dense graded mixtures, and that might be one of the reasons for that. So usually when we add asphalt rubber binder, we might be able to increase the amount of binder slightly. The reason that we didn't actually increase the amount of binder is because, as you may know, in Iran, testing and basically using asphalt rubber is very limited. So it's more or less in the research stage with few field projects. And usually contractor doesn't like to increase the amount of binder, you know, I mean, and they're worried about that. We want to make sure that if they only change the binder to the basically a rubberized binder, what benefits that they can get. And the other point of view that we use wrap to these mixtures is because usually asphalt rubber binder is about 30%, 25 to 30% more expensive than the regular binders, and the mixture is also the same. So when we add wrap to these mixtures, we make those more cost effective, and we want to see really what's happening. Basically, it's like a trade-off. We use a rubber, at the same time we also incorporated wrap to see if we can have a mix with a good performance financially feasible. So in terms of the iFit SCB test, as you see here, we look into the peak load, we look into the fracture energy, also the flexibility index. In terms of the peak load, as you see here, we have a reduction in the peak load when we replace the 8500 binder to the AR binder. But again, it's the peak load increased when incorporated RAP. So at 70% RAP, we have the highest peak load. At the 30% is more or less similar to the control 8500 mix, and 50% RAP is slightly higher than the control mix. The reason that the peak load is reduced for the dense graded mix containing asphalt rubber binder without RAP is, I believe that is more or less because of the rubber particles, which act like a soft aggregate into the mix, and it might affect the peak load values to be reduced slightly, as we see here. So if I want to look into the fracture energy here, as you see, the fracture energy for the 8500 mix, because of the soft binder, is higher than the other mixtures, increasing the viscosity of the binder by using basically AR binder, asphalt rubber binder, reduce the fracture energy, and the reduction also followed by higher amount of RAP. But as you see here, the amount of reduction I can say is not problematic, especially when you see at 50% RAP and 70% RAP, they're more or less similar to each other. Again, that might be due to the use of rejuvenator for these two type of rubberized mixes with high RAP content. The problem here shows in terms of the flexibility index. Flexibility index, as all of you know, is basically the fracture energy divided by the slope on the right side of the load displacement curve from the SCB test. So we have a huge reduction in the flexibility index when we incorporated RAP. The flexibility index of the AR mix is better than the control mix, but when we add RAP, this flexibility index reduced. So we want to make sure that if this is really a problematic a problem for us for using the RAP incorporated asphalt rubber or rubberized mixes. Again, as you see here, for the 50 and 70% RAP, the flexibility index are almost similar and close to each other. There is a slight difference between them. And again, we can explain that by the use of rejuvenator. Basically, using rejuvenator in these two mixes make those to behave similarly compared to each other. In terms of fatigue performance, as you see here, we run the test at 800 microstrain. It's a very high amount of strain for the beam fatigue test. The reason for that, because we definitely want to make the test shorter. We have a limited on the laboratory instrument that we have. So at 800 microstrain, as you see here, the AR70 mix has basically, compared to the other mixes, a lower performance in terms of fatigue. So it has higher initial stiffness and it fades sooner than the others. The control mix 8500 behaves well. The asphalt rubberized mix behaves much better than the others. Basically, even after 180,000 cycles of loading, there is no reduction in we didn't reach actually the fatigue life of the mix. And the reduction in the initial stiffness was about like 40% at this number of cycles. But when we add RAP to these mixtures, the rotting performance of the AR mix reduced. So we can see that here further. The initial stiffness on the left side shows that by incorporating RAP, the initial stiffness increased drastically. The initial stiffness of the AR mix is more than the control mix with 8500, the conventional mix. And on the right side, you can see the fatigue life that we calculated. So the AR mix without RAP passed even like, as I said, 180,000 cycles of loading without any damages. But when we add RAP to the mixes, as I said, so it reached to the fatigue life soon. And I'm not sure that really what's the reason for the 70% RAP here, that we have a higher fatigue life, in more or less because of the basically repeatability of the test. I cannot claim like a benefit for 70% RAP here that increase the fatigue life again. But what I can say in general, that when we add RAP to these rubberized mixes, the fatigue life from the test result that we have reduced. So in terms of rotting performance, as you see here, the rotting performance increases when we add asphalt rubber. We replace the binder with the asphalt rubber. It increased that by about like 3.5 times increase in the flow number. When we add 30% RAP, so the fatigue life also increased. And the properties of the mixes with 50 and 70% RAP are almost similar to each other. They have very close flow number compared to each other. The shape of the accumulative strain versus loading cycles are similar to each other. Again, that's proved the idea of using rejuvenator for the high RAP content mixtures, and showed that these two mixes in regards of the RAP content have similar binder properties because of the rejuvenator that we added to these two mixes. So if I want to finalize what we observed here in this study, for the moisture resistance, we don't have any problem. So it's suitable for all conditions. For the rotting resistance, we see improvement in the rotting performance by incorporating RAP. For the tensile strength, again, so the ITS increased with RAP content, which also a benefit for us. For the cracking resistance, we see the fracture energy and FI index reduced by incorporating RAP. The rejuvenator may help in restoring some of the properties. And for the fatigue life, what we observed that basically the mixes with RAP has a lower performance, but the mixes with 70% RAP is a bit better than the others. Again, I can say I cannot claim any specific benefits for this. We need more tests to make sure that really at 70% RAP, the results are consistent and we get a better performance compared to other RAP contents for these mixtures. And finally, we give this basically conclusion as a recommendation for the industry that they can use high RAP rubberized mixes even at 70% RAP for the hot climates, usually in the south parts of Iran and in the desert regions. We don't have that much of a problem with cracking, and that might be a benefit for us to use even urban pavements for the high traffic area, like in bus rapid transit lanes. It's good to use the high RAP content rubberized mixes. Lower amount of RAP can be used in the rubberized mixes in the regions that we may have a problem with cracking. And we can actually make sure that that might be work appropriately. Definitely, this work needs more research in future. We need to actually have some field section to make sure that what we observe in the field is similar to what's happening, and what we observe in the lab is more or less similar to what we have in the field. So again, these are the research team that we have at the University of Tehran. So my students are really happy that have this opportunity to share their research with this group at the RAR 2025. And I'm happy to basically hearing your comments and questions, and hopefully I can answer those. Thank you very much.
Thank you, Zia. Would you be continuing the presentation, the next one? And then
Do you want me to continue the
I
second
think so.
presentation after that?
you want, okay, we can take a couple questions now.
Uh-huh.
Yeah. Yes, yeah, sure.
Okay.
For a great presentation, thank you very much. Dr. Zia Alavi. Yep. I have a question about using high RAP. In the United States, they have some cracking problems.
So,
Is that closer? Okay.
no, I can hear you.
So
I can hear you.
Thank you. Yeah. So in your case, I think your experiment shows that with higher percentage of RAP, their fatigue life got reduced. I think you're addressing it using Rejuvenator. In the US, they also try to use a softer binder, so you can do a blending chart, figure out what's the optimum binder type and amount they're supposed to use. I'm wondering, in your mix design, what is your insight about using, how do you come up with optimum binder content for that? Thank you.
Oh, sure. Thank you very much. So what I can say is that, what we did at the beginning, we get the wrap and extract the wrap, as you said, in the blending chart. And then we know that at the amount of wrap, like more than 25% or 30%, usually the software binder may not work appropriately. So we need to use Rejuvenator to improve the properties. So what we get, basically, we collected the wrap, we collected the wrap, we extracted the binder, and we tried to add different amount of Rejuvenator to this wrap to see how much we can restore the properties to the 8500 penetration grade binder, which is like the basically base binder using the asphalt rubber. So what we found that with the type of Rejuvenator that we used, 4% is appropriate for the 50% wrap mixes, and the 9% is appropriate for the one with 70% wrap. At the 30% wrap, basically just having the fresh binder in the asphalt rubber or conventional mix is enough to soften the edge binder in the wrap and making that appropriate for the mix. Again, as I said, so I believe that in future, what we found here from the fatigue performance, we should not only rely on the softening point values to find the optimum dosage of Rejuvenator. We might be able to try some extender oil or some other type of Rejuvenator. Again, Rejuvenator are expensive in Iran, so maybe extender oil could be a good option. It's also common in asphalt rubber binder in California. They might be help also in restoring the binder properties at the same time. I hope that I answer your question.
Okay. We can take up other questions after he finishes the next presentation. We'll just ask him to continue. I have a couple questions for you later on, but I think you should continue with your next presentation. Please go ahead.
Okay. Okay, thank you very much. Let me open the second one.
Are you having any difficulties?
To help me actually having these two presentations at the same time. So
Oh, good. Okay.
yeah. So let me share it again. Can you see the presentation now?
We are yet to see. Yes, we can see. Please go ahead.
Sounds good. Okay, so the second research that I'm going to present here is the research, again, that we did at the University of Tehran with 12 of my former master students, Ms. Fatima Labafi and Mrs. Farna Saadat, is about sustainability and performance evaluation of rubberized mixtures using different production methods. So again, the outline of the presentation is introduction, LCA framework, methodology, life cycle inventory, results, and conclusion to wrap up the presentation. So if I want to give you an introduction, so we all know that what is the sustainability and why we need to consider sustainability concerns in using technologies. So sustainability comes along with basically overlapping of three main things: social perspective, environmental impacts, and economical evaluation. So overlapping all these three together comes up with technologies that are more sustainable. Basically, we fulfill our needs for the current generation, and we make sure that we are not jeopardizing the future generation needs in basically using these technologies. So the research purpose here is to see comparing the rubberized asphalt mixtures producing in different methods: dry process, wet process, and terminal blend binders, with a conventional mix in terms of performance evaluation, environmental impact assessment, and economical evaluation. So I should mention that for the economical evaluation and environmental impact assessments, we use basically the current condition in Iran, in the industry, and the price lists that are common in Iran for come up with the price of the production of this material. And for the performance evaluation, we rely on to the several research that done over years and decades on different types of asphalt rubber and conventional mixes, in addition to getting some information from the experts in this field, local experts in Iran, and also the international perspectives from the, as I said, the papers, reports, and also some of the experts. So if I want to give you an idea about how much of these different types of production methods of rubberized mixtures are common in US, there is a research done and mentioned that among the different agencies and contractors that use that are involved in paving operations, 7.3% of them they have experience of using wet process asphalt rubber binder on rubberized mixes. About 54.5% of them have an experience of using terminal blend, and only a limited amount of them, like 13.6% of them, using dry process mixes. I know that in recent years, basically the dry process by using the engineered rubber are trying to get more common, and it's appealing for the industry, especially in Iran. I should mention that dry process is easier to use. So if you come up with a method that we make a good rubber, basically like the works that Dr. Amir Qabusi did in Iran, to process the rubber to make it better and dissolve into the mix in the dry process, that might be a benefit for us to extend the use of rubberized mixes in pavement operation projects in Iran. So for the production method, we know that for the terminal blend rubber and the binder and perhaps some additives mixed together in the terminal, in the refinery, and we have a sort of a modified binder. I prefer to call it like a rubber modified binder instead of the asphalt rubber binder. And it can be used similar to the polymer modified binder in pavement operation in the dense graded mixes, similar to what we have for the polymer modified one. For the wet process asphalt rubber, usually all the process done in the asphalt plant, or basically they have a site for making asphalt rubber binder by making binder and rubber particles and mix them together to make the asphalt rubber binder, and using that at the same day to make the rubberized mix, usually in open grade, usually in the gap graded mixes. And for the dry process, the process is easier, but the properties might not be similar to the others. So again, everything's happening in the plant. We add binder to the blend of aggregates and the rubber particles. and make sure that we finalize in having a uniform mix with good performance properties compared to the conventional mix. So for the life cycle assessment, what I should mention that we should know what is the frame of life cycle assessment for our evaluation. So material production has some environmental impact, basically collecting aggregates, asphalt binders, cement, fiber, steel, and all the other things have some environmental impact. For the pavement design, basically designing of the layers and the thickness of the layer may cause different environmental impacts. And for the construction, all the things that involve in that, having some fuel consumption and also pollution, pollutant produced. So like placement, mixing, scrapping, rolling, and all this. And then end of life, and then like maintenance and preservation over time. Each of the pavements required like preventive maintenance and rehabilitation to have a good performance. And in the usage time, basically, there are also vehicles passing the roads, and all those may cause different environmental impact. And the end of life is basically recycling or dumping the material into the landfill. So this is the overall framework. Based on this, we should know that which part we should focus on for the life cycle assessments in this study. So first we need to find the goal and the scope, the inventory of the life cycle assessment, and then performing the assessment basically at the end and interpreting the results. There are different types of LCA assessment: cradle to grave, cradle to gate, cradle to lathe, and partial LCA. Here what we have is basically a cradle to lathe, basically from the excavation and collecting the material to the end of construction before opening the pavement to the traffic. So what we focus on is cradle to gate assessment for the LCA. The mixes that we actually trying to compare to each other is the conventional hot mix as well with integrated derivation, a rubberized mix produced by wet process, a rubberized mix produced by dry process. The wet process one is using asphalt rubber binder, and the other one is the rubberized mix produced with terminal blend binder. So the LCA study that we did is for 1,000 ton of asphalt mixtures produced, and this 1,000 ton is quite enough for paving a road with 1 kilometer length with a thickness of 5 centimeters and a width of 7 meters. So all the data that we have here presented in the future slides is for 1,000 tons of asphalt mix production. So as I said, we look into that from three main aspects: technical performance, economical evaluation, and environmental impact. From the technical performance, we look into the cracking resistance, fatigue resistance, rotting resistance, and moisture damage, and score different type of mixtures accordingly for these different performance aspects. So for the economical evaluation, we use the standard guideline and the price list for the pavement project in Iran. Cost estimation is for the aggregate binder, fillers, and the cost estimation for the mixture production and placement. And we finalizing this cost estimation by using the basically uniform annual cost over the service life of the pavement to have a more fair comparison among different type of mixtures. And for the environmental impact assessment and the LCA, we use SIMAPRO software and we use the inventory data in the SIMAPRO software to calculate the annual pollutant emission and quantifying those values and comparing different mixtures and scoring them compared to each other. So what I should say as of the framework, for the material production, we said asphalt binder, aggregate, and rubber sugar. So they are about like far from the asphalt plant. Asphalt binder comes 300 kilometers away from the asphalt plant or the refinery, or the place that we produced basically asphalt rubber or terminal blend binder. Aggregate came from like 50 kilometers, and then in the asphalt plant, so we have a batching plant, asphalt batch plant. We calculate the thermal energy required for mixing, and the mixtures and thermal energies required for producing asphalt rubber binder in the plant. And for the construction stage, we said the construction site is about like 40 kilometers far from the asphalt plant. We assume that. We use paver, dump truck, wheel truck, and pneumatic rollers and steel rollers. I should mention that for the rubberized mix, usually the asphalt rubber binder in dry and wet process. Usually pneumatic roller is not basically appropriate for this operation, and only the steel roller are commonly used. So these are the mixtures that we evaluated. As I said, so the amount of aggregate fillers, sand, gravel filler, and the asphalt binder came from like typical mix design documents that we have in Iran, or for some of the mixes like the RHMA mixes came from like validated sources that have the mix design data. So as you see here, like the binder content for the HMA, we consider is 5.3%. For the RHMA dry and the RHMA wet, using asphalt rubber binder, the amount of binder is higher, about like 7%. And for the terminal blend binder, we consider that to be similar to the conventional HMA, just replacing the binder to that, because it's more or less like a polymer modified binder. Is the binder content is 5.3%. So this is what we have, and the amount of rubber. I should again mention that the amount of rubber in the RHMA dry and wet process are the same, and is about 20% of the weight of the basically binder in the mix. And for the RHMA terminal blend, usually the rubber content is lower, is limited to 10% of the binder weight. So machinery operation and the times for paving this 1,000 kilometers for 1 kilometer of road, as I mentioned. So for 1,000 ton, it's like this. We consider like 10, 20, and 30% increase in the time for using RHMA, because they might be more difficult to basically construct the road using the rubberized mixtures. And we consider also this with this interval, 10, 20, and 30% increase in the time of operation. And as you see, like these are different data for the time usage of the asphalt plant for this 1,000 ton of material and all the other things. And one I should mention here that for the RHMA wet process making asphalt rubber binder, we consider mixing the aggregate, mixing the rubber and the binder at 190 degrees C for 1 hour. For the terminal blend one, we consider that 2 hours at 220 degrees C. So these are comes from, as I said, reliable sources that we discuss, and to see what is usually happening in the industry when they make asphalt rubber binder or terminal blend binder.
Would you mind wrapping up quickly, Zia, because we are running out of time?
Definitely.
Yeah.
Definitely. I'm sorry. So again, here is again the flowchart for same data that I presented before. So what I should mention about like the scoring in the technical performance, as you see here, for the fatigue life rotting and the moisture damage, we come up with the numbers for that. For cracking HMA, we consider all that as a baseline, as one. When we add rubberize in the dry process, 20% increase in the cracking performance, again, like fatigue life, 1.7%. And for the rotting, the same, like 20% or 40% and or 50% for terminal blend. And moisture damage, similarly, you can see here. Finalizing that, I can come up with a normalized score, as you see here. the rubberized mixes with terminal blend binder get the highest score, 100, and the lowest score for the HMA, which is like 73.3%. And the wet process and the dry process are relatively similar to each other, but wet process is higher than the dry process. For the economical evaluation, as I mentioned, we consider the cost for the production, and we make the cost as the equivalent uniform annual cost. Basically, we come up with the cost, we consider a discount rate of 10%, and we find the equivalent uniform annual cost over the life of the payment. We consider the life for HMA to be 10 years, and for the other mixtures, as you see here, for the RHMA dry is 1.4 times higher, for RHMA wet is 1.5 times higher, and for RHMA terminal blend is 1.25 higher than the basically the time the lifespan of the HMA. Again, normalizing scores shows that the RHMA wet process with 10% increase in the machinery has the highest number, 100, and the lowest was for the HMA, which is 89.4. The dry process and the terminal blend are more or less similar in terms of the equivalent uniform annual cost. Environmental impact assessment, again, done in different fields like global warming, ozone depletion, on human ozone formation, mineral resources scarcity, and fuel consumption, which is a fossil resources scarcity. So as you see here, for the asphalt rubber in terms of wet and dry process, the values are higher than the conventional mix. For the terminal blend is a bit higher than the conventional, but more or less similar to that, and more than the other two types of rubberized mixes. Again, in terms of human health, ecosystem, and resources, you see more or less the environmental impact is on the human health, not the other two factors. And the highest values are for the dry and the wet process rubberized mixes compared to the other two conventional and terminal blend mix. So again, like the normalized plot shows here that we find that if we want to look into only the pollutant at the time of construction to at the time of production to the end of construction, the values for the RHMA wet process is higher than the others, and the dry process is similar to that, then followed by the terminal blend, and at the end is the HMA. But we have to consider that the lifespan of different mixtures are different. So we divided this amount of pollutant to the number of years of the lifespan and find values like the pollutant of CO2 equivalent per year to the lifespan, and we found that if we consider the lifespan, the RHMA wet process is better than the others, and the lowest is for the HMA. Basically, for the HMA, it means that every 10 years we produce this amount of pollution, but for the RHMA wet, every 15 years we produce this amount of pollution. So because of that, we said the RHMA mixes are more environmental friendly considered to the other compared to the other two type of mixes. Here again, like the environmental impact assessment, similar data presented here. I just want to wrap up the presentation. At the end, I should say that from the technical performance, dry process has 20% increase, terminal blend 27%, wet process one has 23% more increase in the performance. In terms of the equivalent uniform annual cost, the wet process one is better than the others, and in terms of the environmental impact assessment, we said that we found out at the end that the RHMA mixtures are more environmental friendly. What I mentioned here that overall we may know all this data, but we're trying to produce this data again for Iran to make sure that we can convince the industry and agencies to use the asphalt rubber binder, because really they are scared of these things because of the cost, and at the same time they don't know really the. First, we need to actually convince the agencies to support these new technologies and make sure that the industry also accept this new technology. Here again, my team for this research, Ms. Fatima Labafi and Mrs. Farna Sadat, and I also basically lead this research. Thank you very much. If you have any question, I'm happy to hear and probably answer those.
Thank you. Thank you. One round of applause for Zia Alavi. We have time only for one question. Yeah,
Sure.
only one question because we're running out of time. Thank you.
Thank you very much, Mr. Alawi. I have one question. If you imagine that you are totally on the starting point, which method for the production you will choose? So you have no experience, you are starting with rubberized asphalt, so which method you will choose, what you can say?
Okay, I get your answer. So, well, what I should say, I mean, research shows that terminal blend and asphalt rubber binder mixtures are good. But what I want to say in terms of industry and involving the industry as well here, we are really scared of using this technology, to be honest with you. Terminal blend binder, the refineries, it's really hard for them to produce this binder. They are worried about the storage stability of the material, and they are worried about the making sure that the properties always meet the specification requirements. For the asphalt rubber binder, the problem is there is a lack of basically a specification to make sure that asphalt rubber binder produces consistently with the same properties. So what I mentioned, what I would like to actually support in future, and we are working on that to see if we can engineer the rubber that we can use it in dry process, not just directly adding rubber. Perhaps we need to marinate the rubber with some extender oil, or basically trying to treat the surface of the rubber to make it better. And one other option that I'm suggesting to use is making some concentrated asphalt rubber binder with higher amount of rubber that they can add it to the plant easily, and making the modified rubber binder to produce. So to answer your question, I prefer to start with a dry process engineered material for the developing countries.
Okay, so Zia, we have Dr. George Souza with a comment, please.
Fantastic question. Thank you, very appropriate. And as you saw, he is proposing that we pre-engineer, pre-cook the rubber, so then it can enter as dry process. That's
exactly.
So that's what we have been presenting here, and there is in US they have something called Smart Mix, and in Europe and they developed something called RAR2025, which you can see and find. So,
exactly.
but what he's saying is the normal evolution, because of the problems of the terminal blend. Pretty much you destroy the rubber, so what do you want to do it for? With tremendous energy costs. The dry process, the normal wet process is very good, but it adds this annoyance of having another hour cooking the rubber before being delivered, and if you don't use it, then it's destroyed. That's why we end up developing this pre-cooked rubber. So that's what I recommend you look into.
Yeah.
Sorry.
No problem. I just had a comment, Zia Alavi. You haven't done any multi-parametric optimization with performance, when you say performance, the mechanical performance and the environment. So, sorry.
I'm so sorry to interrupt you, but someone yesterday left the purse in the restaurant.
Yeah, she'll be here soon.
So you know her?
Yeah.
Can I give it to you? Yeah. All right. There's a witness here. It's being given.
Yeah. Yeah, so I just had a quick comment. Maybe we should try the multi-parametric optimization between the mechanical performance and environment, because you have a lot of negative performances, even including the fracture, right? So
Sure.
I think you need to go a different route on this, because it's not actually correct what you're getting there. It'll be the opposite. You should be getting the positive results. Anyway, okay, so thank you very much, Zia Alavi, for your two presentations. Very important starting phase right now in Iran, I'm supposing.
Sure.
But if you want to continue staying with for the other presentations, you may do so. We'll continue with the other two.
I'm
person.
following you through the YouTube channel.
Okay, very good.
you.
Okay. very
Okay.
good.
Thank you. Thank you very much.
Thank you. Thank you. Thank you.
Appreciate it. Okay.
Yeah,
Bye-bye.
yeah. Okay, so we'll continue on with two in-person presentation, one by Kawande and team on compatibility and performance assessment of asphalt rubber binder activated with waste cooking oil, presented by Mataparthi.
Thank you. Good morning, everyone. My name is Sri Gangadhar Mataparthi. I'm a PhD student from Indian Institute of Technology, Tirupati. Today, I'm here to present the research work, Compatibility and Performance Assessment of Asphalt Rubber Binder Activated with Waste Cooking Oil. This research work was carried out by Vatsalya and Shobhit Jain. They are my colleagues at IIT Tirupati, and it was supervised by Krishna Rapuna Bilgiri, who is the chair of this session as well. So last couple of days we are discussing the advantage of incorporating end-of-life tires into asphalt binder, which reduces the landfill issues, enhances the durability, improves the performance of the pavements, and lowers the emissions. Along with that, we have some certain challenges associated with asphalt incorporating crumb rubber in asphalt pavements. Some of them are mixing and compaction temperatures, which are very high in case of AR pavements, which can be mitigated with the Warmix technologies. And durability issues and compatibility issues. Compatibility issues arises due to the difference in the specific gravity of the rubber particles in the asphalt binder. To address these compatibility issues, can the waste cooking oil be a solution for this? So why incorporate waste cooking oil with asphalt? Studies have shown that there is a good cracking resistance. Low temperature thermal cracking can be mitigated with the use of waste cooking oil. Along with that, the waste cooking oil, when mixed with the or blended with the crumb rubber, it gives surface activation, it improves workability, and it is a part of sustainability aspect as well, because there are million tons of waste cooking oil generated through cooking industry, kitchen every day. So the crumb rubber with asphalt have a high performance. But the problem with the incorporation of crumb rubber with asphalt is the higher production temperature and incompatibility, whereas waste cooking oil with asphalt improves the lower and intermediate temperature performance, but the lower production temperature and improved storage ability are some of the advantages with waste cooking oil. So when we blend the crumb rubber waste cooking oil with the asphalt binder, can we get this durable or sustained pavements? Let us see this. So the major objective of this study is to enhance the compatibility between crumb rubber and asphalt binder in air binders using waste cooking oil as a compound activator, as it can simultaneously act as a softening agent and promoting chemical interaction between the components. The scope involved preparation of modified binders through two addition methods. One is direct addition and the other one is pre-treatment method. And the second scope is selecting the optimum combination of this crumb rubber and waste cooking oil in the binder modification, and finally assessing the performance using mixture performance testing. So the waste cooking oil that was used was soya bean waste cooking oil, which was fried 3 times to match with the industrial standards, and then this was blended with crumb rubber and asphalt binder. As I mentioned, there are two addition methods that was followed. One is direct addition of waste cooking oil and crumb rubber into the hot asphalt binder, which is very much equivalent to a wet process of asphalt rubber production. And the other method is the crumb rubber is pre-swelled with waste cooking oil. First, the crumb rubber and waste cooking oil, they are blended in a ratio of 4:1, 3:1, 2:1, and 1:1. They are heated for a certain amount of time, and then this blend was mixed into the asphalt binder after the swelling and treatment stage. So after these two binders addition methods were used to collect the binders, and then the binder testing was performed and the mixture testing was performed. to check the performance metrics. As you can see, the methodology followed compatibility assessment. One is the preparation of binders and then coming up with the performance metrics. The directly added, this is the high temperature performance grading. As you can see in the direct addition method, without any waste cooking oil, the 20% crumb rubber gave the highest PG grade of 82, whereas in the treated method, it gave about which that is about 70. If you can see, with the increase in the ratio, there is a decrease in the PG grading, which means that the waste cooking oil is much more acting as a rejuvenator in the binder. Then the viscosity was performed, where you can see the VG30 viscosity is around 800 centipoise, which is very well in the workability range. But if you see the 20% crumb rubber with zero waste cooking oil, the viscosity rose to about 17,000, which is very much difficult in the field to use it. So with increase in the waste cooking oil content, the viscosity decreases gradually. If you see the 3:1 ratio, the viscosity is in the balanced range. Then the separation test was performed, where you can see the separation difference between the top and the bottom layers. You can see in the direct addition method, there is much more variability compared to the treated method. In the treated method as well, with the increase in the time of cooking or addition of this crumb rubber and waste cooking oil, there is a decrease in the separation index. The 3:1 ratio with 60 attained minimum, 4 degrees Celsius difference, which is very much acceptable. So based on these test results, it was confirmed that 3:1 crumb rubber and waste cooking oil binder treated for about 1 hour at 200 degrees Celsius was found to be optimum. This optimum content was used in the mixtures, and then the dynamic modulus was performed, where you can see at the lower end, there is a very much low temperature cracking resistance with the use of waste cooking oil. So there is a balance between stiffness and flexibility using this waste cooking oil in the mixtures. Semicircle bending test was also performed, where you calculate the fracture toughness. At both the 0 degrees C and 10 degrees C, the 3:1 crumb rubber waste cooking oil mixture showed superior and consistent low temperature crack resistance and outperforming the conventional mixtures. Hence, we can use this pre-treated crumb rubber with waste cooking oil into the asphalt binder as a mitigating strategy of these compatibility issues. And the 3:1 ratio of crumb rubber with waste cooking oil, which was blended for about 1 hour at 200 degrees Celsius, was found to be the optimum. And the modified mixtures showed better performance in terms of flexibility and stiffness as well. Hence, we recommend the use of waste cooking oil in the certain ratio to achieve the balance between sustainability and performance metrics. Thank you.
That was quick. So if you have a question, one question. Time for only one question. I know you didn't do the work, but just wanted to ask you, maybe asking the team. When you say you're using waste cooking oil in rubberized asphalt, so do you think it's a pre-activation or it's an activation?
It's a pre-activation method.
Why do you think it's pre-activation? Why not activation?
The rubber and the oil, when they are blended, the oil is giving the properties or enhancing the properties of the rubber surface. So it is pre-treating the rubber, and then we are using it in the binder. So I guess it is a...
There are two methods.
Yeah.
Right. Okay. Fair enough. Okay. Thank you.
Thank you.
Thank you. We have the last presentation in this session before we go into keynote. We have Mr. Singh from California. Let's see, try to open this. So the title is Utilizing Turf Rubber Infill in HMA by Professor Ding Cheng, Director of California Pavement Preservation Center, and also Professor at California State University, Chicago. Over to you, Professor Cheng.
Thank you, Professor Christina. Good morning, everyone. I hope you all have a good event yesterday and especially last night. That was really enjoyable. Today, my topic is utilize turf rubber infill into hot mix asphalt. And this is a request from CoRecycle, is an environmental agency from California, because in the United States, each year around 1,000 field is a sports field. And in the sports field, there is an infill, as you can see from here. And then there is a grass. Underneath the grass is infill to protect the athletes, right? At the end of life, they need to be recycled. Instead of putting into landfill, let's think about something else. Then this one way as a pavement engineer, and then we try to see is it feasible to utilize them into hot mix asphalt. Right? That's where we can reduce greenhouse, right, and then promote sustainability. Okay, in this particular study we do for CoRecycle, basically we utilize the knowledge you all know here since 1960s. Then Arizona, and then California. A lot of pioneers in this, especially in this RAI conferences, and then they come up with different solutions. So over the years, you can see so much development in this field. And then really, we want to see, well, can we do that with chrome rubber infill materials? Okay. Unfortunately, so far is not people using that technique yet. That's why we want to utilize the technique we have to see is it feasible or not. Okay. And then we try different approaches. So our plan is we want to see any simple solution can be found, right? We start with simple because we are engineers, try to minimize cost. So one approach is a dry method, and another approach is wet method, right? So we can just try these two approaches, and then we're going to do some laboratory testing, and then try to use the DOT, like Caltrans, California Department of Transportation, their mixed design methodology, their test. That way, if it works, we can do a trial. So first, we start with the dry method. Our dry method is try to make it simple, and then we get a source of material. We try to figure out how to make this source workable. And then first thing we did is some gradation analysis, make sure that we can create a volumetric mix design from the gradation. And then we incorporate into this chrome rubber infill into the hot mix asphalt based on volumetric characteristics, right? So we can do a super pave mix design with volumetric methodology. And then we got a binder, just get in our Northern California, Sacramento region. We use PG performance grade 64-16. So highest temperature is 64 degrees Celsius, and low temperatures -16. And then in the lab, first we ran some super pave binder testing to verify what we got, right? And then we run at a 64 degree and then 70 degree, and original binder, neat binder, and then we run RTFO. We verified the binder, it has 64 -16 binder grading. And then after that, we try to figure out how we're going to incorporate this thing into the hot mix binder mixes. So we started go to one of the contractors, and then get the existing mix design that is working for them, just as a control mix. So this mix design does not have any chrome rubber yet. So you can see that they have 6 bins. So each bin has different gradation. When they try to create their mix design, they have a proportion for each bin. When they blend it together on the right side, they will meet Caltrans volumetric design requirements. There was an upper limit, there's a lower limit, right? From there, they can get their basic aggregate gradation. Okay, this is a 3/4 inch, which is a workforce. Most of the dense grade hot mix asphalt, they use this 3/4 inch hot mix. The next step is try to incorporate the chrome rubber infill into it, right? But before that, we're checking there again, checking the mix design in our laboratory, because the mix design from the contractor sometimes may be different from what we have, although we have the same material. We have the donated material from the contractor. And then, but we just verify them. The mix design basically goes through the volumetric mix design process. You get air voids versus density. They have theoretical density and then bulk density. Figure out what is a VMA, what is dust proportion, so on and so forth. Everything looks great, so we proceed, right? Proceed into try to utilize the rubber infill. And then we got multiple sources of infill. We went to different sports fields and then collected the samples from them. As you can see, different field, the rubber infill are quite different. And then the turf one, they still have, you can see some of the grass, a lot of grass will be into that. It's hard to separate the synthetic plastic grass with the rubber, right? The first one, the turf one. But it's okay, right? You have a little bit plastic. It may or may hurt the performance. We'll see. And the turf 2 is cleaner. It's more like what we have from some of the manufacturers in terms of chrome rubber infill, chrome CRM material. And then turf AB is another field. And then we go there, we ask them to try to separate the rubber infill from the sand, but it's quite challenging in the field. So we can see some blending of the sand with the rubber infill. So those are provided challenges if you want to do, utilize the chrome rubber infill from the sports field, and then those are the things you're gonna meet. And then we study the gradation of them, try to figure out what kind of material we got, what kind of sizes they are, and then from there we start to figure out what kind of a blending we want to utilize, right? So here's the 3 choices. For turf 1 or turf 2, we found 3% seems like is a good blending percentage. And then for turf AB is 2% and 3% by weight of the total mix as our blending amount. And then based on the gradation we have, sometimes we also need to figure out what are we really adding into. For example, this is another source called SS1, which has blends of chrome rubber plus sand, right? And then when we incorporate them, we need to think in both. Both the rubber going to affecting the performance and the additional sand being added may change our gradations. So that's the things we need to study from our material we received. And then for the white method, so basically we're trying to figure out how can we make some maybe like asphalt rubber, right? Goes through this white process first of all, we need the processing our materials. The material we got have sand, have grass, right? So we need to separate them. The methodology we use based on the special gravity differences So we use gravity separation methodology to separate out the chrome rubber. And after we got the chrome rubber, we blended with virgin binder like PG64-16, right? That was used for the project. And then we followed the wet process blending procedure in the laboratory with high temperature, right? With at least 45 minutes of blending and then checking the viscosity. And then through the process, we feel there have enough interaction between the rubber and the binder, and then we created our rubber binder. Okay, and then we can start to utilize that as a rubber binder as our research process. There definitely modification because of the chrome rubber. Similar effect you can see when we run the DSR test. So we had run a DSR test on the different aging stages. The original binder, as you can see from this graph, for our original binder PG grade, we only can run up to 70, but with rubber infill blended binder, we can run all the way almost to past 88. So you can see the same trend of you're increasing the high temperature grades because of incorporating the chrome rubber infill. And then similar trend shows up when we did the wet process and with RTFO aging on the left side. As you can see, we actually did one more step. That will be another study where we're trying to figure out what is UV aging instead of just aging through the oven. In our lab, we also have a UV aging oven. So try to figure out how much that can impact this particular material. As a matter of fact, I do see a big impact on the high temperature performance if you after UV aging on the material. And then they have the same trend. They can pass it all the way almost 94 degrees Celsius for the high temperature. And the phase angle part, phase angle alone also shows the lagging angle, between the elasticity and the storage. So phase angle itself also shows some improvement because phase angle got reduced because of the additive of chrome rubber infill. And then we start volumetric mix design, right? We start to think about how we're going to incorporate them into it. In this case, we did require us to modify the gradation a little bit. The reason for that, now we have asphalt with higher viscosity. So in order to use them into our dense grade, we have to bend the gradation a little bit. It is still in the dense grade range. It is not gap graded, but it's a little bit away from Caltrain's the dense grade requirements. And then, but creating that a little bit of gap, we're able to incorporate this chrome rubber infill binder into it. And then we started a super pave mix design, follow the Caltrain's standard process, figure out air voids, GMB, GMM, the VMA, VFA, and the dust proportion. And then we successfully produced the mix design of using the rubber infill binder material, okay? And then we ended up optimal binder is 7.7%, which is higher than the regular conventional hot mix asphalt. Then we conducted some basic performance test. This is a rotting test, basic Hamburg test. Hamburg shows the control material that meet the standard specification. There's no issue, but with our rubber infill modified mixes, we have some trouble actually dealing with it. But it's kind of like expected because we understand this material. We didn't do very much treatments. We basically doing the minimum, try to incorporate into the mix design. But we still see some differences, especially for turf AB. on the left side, it has a pretty good performance in terms of Hamburg test. The real advantage is come with the cracking resistance. So in US, there's the balanced mix design become popular, right? And then in California, there's the long life payment requires like a 4-point beam testing, but regular overlay, they don't require that. But ideal CT is one of the indirect tension, cracking, looking at cracking energy, dissipated energy, fracture mechanics. So this is a good test for a simple, quick mix design. So we did this test on this material. We really found some advantages. So this chart shows the CT index, and then we have the 3 samples, the modified binder, and generally the CT index in the middle. For Caltrans material, they say need to be 90 or above. But look at the number we got, 700, 800, 300. Wow, that's great. Even very simple addition of the chrome rubber into this binder material, we'll be able to achieve 8 times of improvement in terms of cracking index, right? Ideal CT index. So that's really the advantage of this particular material, even though it is preliminary, but it shows some promises, right? So what we see from this study, basically, it demonstrated it is feasible to incorporate chrome rubber infill material, especially we saw the advantages with the wet method, right? Because it significantly improved the cracking resistance in terms of ideal CT index. And even the dry method also provided some good advantages in terms of using this particular material. The downside of the currently utilized this material is the rotting test. The Hamburg test, right, is under 50 degrees Celsius, underwater. You went through the 20,000 passes. We call it torture test on the hot mix asphalt, right? So this, we still have some issues, right, need to be improved. But one of the things we can think about utilize this material is thin asphalt overlay. You just as a surface layer, you underneath have foundation resisting the rotting. The top layer really is protecting underneath and also reduce reflective cracking. And if you have a very high CT index, that exactly is what we want, right? So it really has some advantages of utilizing this material. So our recommendations, and then basically, we do see a lot of variations in terms of source. They come up with different compositions. So you do need a mix design procedure to make sure you use the material correctly, right? And then also, it has promising ideal CT results, which can be utilized in the future. Say, we can utilize this material into hot mix asphalt. And the future research should think about additional ideas, especially from this conference. There's a pre-treatments, created dry pellet products, additional ways we can further improve both cracking resistance and rot resistance. So that concludes my presentation. Thank you very much for your attention.
Thank you. So we can take up one question, and then Professor Cheng is here for questions later on. Yeah. Please go ahead.
Thank you for a very nice idea. I have a question that if you follow the football authorities' recommendation for infield in football pitches, you start with a layer of sand, and then you have a layer of rubber. And when you recycle the infield, it's difficult to get the sand out of the material. So how do you crack that nut to take the sand out? Because I realize it's probably not an ideal ingredient in your combination.
Yeah. Thank you for, you play soccer or play real football? Soccer.
Yeah, I do, yeah. But I'm from Guinea, and we supply the rubber for infield.
All right, sounds good. So we work with a contractor in the field. So they have a machine just to recycle the sports field. So they have a big suction. When they run in the field, they have some cutting, make sure it's in their vehicle width is about like 10 feet each row. And then they roll off the turf first. And after turf, then exposed underneath has the infill rubber, underneath the infill mother has the sand. So they adjust the suction, so they try to get as much of the clean rubber they can. So this is for us. So before that, they don't care. They just dig everything out and then put it in the bag, and then we're done, right? So now I need a bag of just rubber, and then I just rise of a bag of the sand. So you have some good manufacturer of equipments, they can figure out how in the field just get a rubber only or smaller amount of sand, things like that. Yeah, thank you.
Okay, very good. Thank you very much. And one round of applause for Professor Cheng once again for a nice idea. Thank you. Thank you. So we have a demo of the Taiwan Innovative Rubber Project.
You want to show the one video first?
Yeah, exactly. Okay. So I'll open this one, right? KHD.
Is
this or this?
this only?
This, yeah.
Okay, and USB.
I think this is a video.
Can we have?
We don't want this?
yeah.
This one? Yeah. Okay, over to you, please.
As global warming
stop?
gets worse,
Sure.
countries have committed to achieve net zero by 2050. Founded in 2007,
Is this the one you want to show?
Yeah. Just a moment. Okay. Hi, everyone. My name is Steve Chen, coming from the Taiwan KHD company. It's my pleasure to introduce our innovative design, material design for cold mix. We are pioneer in Taiwan to conduct our cold mix solution in highway and local road. Before my presentation, I will please take a look at the brief video for our company product solution and our company introduction.
as global warming gets worse, countries have committed to achieve net zero by 2050. Founded in 2007 through our ESG and Target Forward commitments for sustainable development, KHT Asphalt Plant first installed local scrubber systems to filter out air pollutants, was the leading producer to use natural gas burner fuels instead of heavy oil, and the first to have data transparency online with the Environmental Protection Bureau. Now, we're an early pioneer in Taiwan, launching the state-of-the-art technology of cold-mixed recycled paving material and cold-mixed new aggregates for road pavement application. Conventional asphalt concrete is a combination of two primary ingredients, aggregate and asphalt cement. During the high-temperature construction of hot-mix asphalt mixture, a large number of carbon dioxide emissions and heat waste are produced with high electricity consumption. In hot-mix production, this causes hazardous substances and long-term health risks, but our best cold-mix solution can improve the conventional drawbacks. Cold recycled asphalt mix has asphalt concrete residues, interface coagulant, retarder, and water-based UV resin. Adding recycled tire scraps helps the pavement surface become more resistant to deformation from wheel rutting, less slippery, quieter, and more durable. Old asphalt can be 100% recycled into new eco-friendly asphalt. Cold mixed new aggregates no longer use traditional asphalt material, but gravel and sand instead, and select different sized particles by specific weight and proportion, combining with coagulant, resin, etc. to complete cold mixing, non-toxic and harmless materials. In addition, cold mixed new aggregates can be compounded into the optimal ratio through the Marshall pavement test. By applying cold mixing production, reclaimed asphalt pavement or new aggregates, all the processes from factory to on-site pavement need to be non-heated and as close to zero carbon emissions as possible, resulting in lower power consumption and fully compliant with greenhouse gas (GHG) protocol standards. Cold mixing asphalt production does not generate harmful substances and features a process that is non-toxic, odorless, and tasteless. The utilization of reclaimed asphalt pavement can help build a circular economy. We use cold mixed new aggregates and cold mixed reclaimed asphalt pavement, which is more efficient and durable than traditional asphalt concrete. Through the Marshall stability test and resistance to moisture-induced deformation, cold mixed new aggregates elevate viscosity 5 times compared to traditional asphalt concrete. Through the Hamburg wheel test, 20,000 wheel passes is far beyond the traditional tolerance. As trusted excellent technology, via green materials and mutually beneficial environmental concepts, KHT Asphalt Plant can realize the ESG enterprise culture and core values to lead domain innovation and provide people safer, higher quality road construction.
Okay. Today I want to introduce our product solution, resin modify web process the comics with the chrome rubber additives in surface layer material design. Why to develop the comics? Because of in Taiwan, our government restriction limit to up to 40% recycling to use for planning waste. But because of the 40% to use, nowhere to go. So it's will getting more and more a large number stock in pile. So that's why we developed a comics to be able to resolve this problem, and also using the comics without heat anymore, and to save the energy consumption. That's why we developed a comics. Our design is to use the 100% reclined and chemical resin as the binder to have the comics mixing together with the aggregate and co-paving in the field. Here's this data compared to our harmless measure using the chrome rubber as a partial replacement for fine aggregate. You can see the first column, it will show the reduce the half and carbon emissions as this data. For chrome rubber additives with our resin modified binder using 100% reclined and the no heat process to reduce the carbon emission. Following, we will introduce our design test procedure and the missing and construction process, and then field verification and how to carbon reduction. For our production process is to use the 100% reclaimed as for concrete through wet process and using our chemical resin with the clam rubber 44% to 6% mixing together and then ready to deliver to the field for payment. Using our solution, the advantage will have the higher ductility, crack resistance, and have the noise reduction, also decarbonization. We have do some lab grading tests by Taiwan University for tensile stress TSR report. Immersion residue stress test reached 94% greater than the standard 70%. It means our material can resist the water damage. Also, we have the indirect tensile test in the first day, starting from first day in the stable state. The performance can meet the requirement of ASHTO and ARRA, the specification. And also the resistance module test indicating the elastic recovery ability and the stress not affected by the long-term traffic load. Here's our production steps and the process, almost the same hallmarks, starting from planning, removal, crushing, refine, and mixing together, and then ready transfer to the field for rolling and compaction. The whole process from manufacturing to construction should be within 4 hours. Here's our mixing process. For corn under the temperature at 25 to 30 degrees C, and using requirement as for payment, and crown rubber 4 to 6%, and our the resin. Here's our production step by 2-step mixing. 1 step is the crown rubber, and our resin is the water-based like curing agent to mix together, have the chemical reaction. The second mixing with the aggregate mixing together. For the field on-site paving, also using co-paving, almost the same hard mix method. For field verification, we conduct specific gravity of compact bituminous mixture, about 98% is greater than 95% in good condition. And also, chemical field tracking test, around our test result around 16,000 times. And we also have the MCI index tracking management to see in good condition the MCI formula here and the data. For carbon reduction, our solution compare in construction. You can see the COMEX better than Hallmark's data. because we can save the power consumption. Thermal emission is zero and no air pollution. We can conclude our benefit to use our Convex co-payment material design. Utility of the crown rubber 40 to 60 kilogram per ton material. If low paving 1 kilometer length, you will have the 900 tons of crown rubber are required. It means the 90,000 waste tires distorting. And using our Convex, we have the 100% RIP for recycling use. Compared to Convex, no heavy oil, no natural gas, no asphalt are required. It can achieve the zero emission of road construction. For further step development, our company are still in developing to incorporate into our Convex with the waste efficient nets, targeting from 1% by reducing marine waste. It can enhance its property like the crack resistance and the durability for road construction engineering. Okay. You are welcome to discussing outside at our booth. We can share our practice and some information. For further information, please, you can email to us for share. Thank you very much.
Thank you. Thank you. Thank you. So that comes to the conclusion of 5 presentations. Now it is my pleasure to invite the keynote speakers. They're here. Okay. So may I now call upon Dr. Ellie Feeney and Dr. Mahur Parist. Dr. Ellie Feeney is an associate professor at Arizona State University School of Sustainable Engineering and Built Environment, and Dr. Mahur, associate research professor at the Delhi Webb School of Construction. So the keynote presentation title is Enhancing Sustainability and Promoting Community Resilience Through Rubberized Roadway Infrastructure. Over to you, Dr. Ellie Feeney. Oh, it's not here. We need to load the presentation. Fernanda, presentation.
Here. Okay.
Okay.
Yeah. Try to speak.
Hello, hello. You hear me? All right. So welcome. Thank you for being here to hear this talk. I want to tell you a little bit, sort of a little bit of different angle of what we have heard, but of course along with rubber applications. Let's take a second and think what we have learned last few days together here. We learned about different rubber applications. We keep hearing the word rubber, right? Different name of rubber. We have from Rorax, as George told us, all the way to turf and mix of rubber. All of them have some sort of rubber in it, right? You agree? but we have different name for it. So when we think and we look at it and we see they perform differently, but when I look at it, they are all rubber, meaning the chemistry, the molecules, the building blocks of them have similarities. So I'll take you a little bit back to what rubber is and what activated rubber or swelled rubber and all this means in terms of performance. This is me. That's my contact, so feel free to reach out now, after, when we leave. I think that this community is trying to promote more sustainable applications for roads. Of course, here we're emphasizing rubber because we believe in it. But overall, from the video you saw, the surprise video that George showed us, is all about community, planet, survival, in a way. We are reducing carbon footprint because we know something is happening, right? We have climate change and all these things we are hearing. So back to that point, how far we came with the rubber. Did we solve the problem? Are we carbon zero, maybe carbon negative? Not yet. So you heard some of the talk from Zia, online talk, talking about emission associated with rubberized asphalt, whether dry process or wet process, and then he compared it with the control, which was HMA. Yes, performance, we all know, that's why we are here. We know the performance is good, and last few days you heard rotting better, fracture is better, moisture damage is better. So we know noise. My colleague from Michigan Tech showed noise reduction, 2.5 decibel. So all these are good. So what else is left to do? That's why I want to talk a little bit about how we can reduce emission to be better, maybe, and cost. So I'll talk a little bit about those. But when you think about it, it's still rubber. It's still the same process. Yes, we are tuning it a little bit here and there. We get the performance, but maybe we're not comparable with HMA on the cost or emission. Why not? Is there room to do more and better? Right now, EPDs, you all know, it stops at the gate. So you literally calculate emission and the cost and energy for the production. But all we talk about is long-term performance. We are adding 5 years here. We are adding to the life 2 years there, and so forth. So if we are extending the life, how we are counting that into current dialogue, which is EPDs at the gate. So maybe we should go back and see how we can reduce that as well. And a little bit about my group, since I consider myself a material engineer, so I look at material of different sense. I think of everything from this jacket to the rubber you talk about as molecules. Even the waste, you talk about turf. Turf is molecules. Like all of them are made of molecules. So for me, there is no waste. It's just the wrong material that are in the wrong place, wrong time. There's no waste. So we can turn everything to value-added products. So some things I work on is climate adaptive design. I work on the smart materials. One thing I'm very interested in is early detection of damage. Sometimes we detect the damage, well, it's very late. When you think about it from the molecular side, you don't have to wait to see it with the naked eyes. You can actually see the damage before we can see it with the naked eyes. That's called early detection, which can reduce our cost, and predictive modeling. So many of the things you think about, like when we talk about rotting, cracks, and all these things happening, why they happen? Do you think if you have this beautiful pavement you made, you put it in a closet and take a good care of it, would it crack? Probably not. So why it cracks is because of environmental stressor, one thing, and George was telling us maybe we can put a solar panel on top to protect from rain and heat and sun and all this. So one way is to protect it, or put it in a closet, don't use it, then it's good. Or come up with a built-in resistance mechanism. So if we know what is exposed to, maybe we come back and build a build resistant mechanism, which is basically what we all do. We're trying to build, and then we test it with Hamburg, we say it's better. Maybe we build some resistant mechanism. But do we know every attack that our roads get to? George mentioned rain. Yes, we know it's gonna rain someday. Sun. What else? What is out there that damage the road? If you're like me in Arizona, I would say sun actually is pretty harsh. When I moved from North Carolina to Arizona, I had to change my sunscreen. That's pretty harsh. You actually have to protect yourself big time. So if you haven't been in Arizona, that's where Arizona is my favorite place in America, where we actually we believe and we claim as being #1 in the US in addressing UN Sustainable Development Goal. And so this is a big achievement, I think, for the university to be in that space. And this is our famous cactus, if you ever come there. And what we do, and my group and my talk here will actually pitch sort of into that, is bio-inspired design. What you see here is our famous cactus, and then what you see up there is a building that is mimic after cactus. So what else? What more beautiful can be that we learn from nature and then we adapt? You may think, why in the whole world you learn from cactus? Well, cactus is very resistant, you know? You can't imagine standing out there for years and survive. If you stay there like this for a day, you're gonna die. So it's pretty resilient. So we learn from cactus and build this building designed and mimic after cactus, which brings back to my group. My group at ASU is Bio-Based and Bio-Inspired Solution Lab. We learn from nature and we go back and design things. So I put this slide there because I want to bring everybody back to this discussion of carbon. I know everybody here on the news, and we always talk about it. George showed us beautiful surprise video, all talking about carbon, carbon, carbon. But why do we think carbon is a villain? Have you ever thought about it? I know we just intuitively we know, oh, CO2 is bad, just reduce it, CO2 is bad. But why? Do you know what's the most expensive carbon you all love? Anyone loves carbon? Come on, we ladies love diamond. Diamond is carbon. So carbon by nature is not bad. And as I told you, I'm a material engineer. I see molecules, I see atoms. So carbon by nature is not bad. Why we think and we believe is no, it's too much, we have to reduce it. Let's reduce CO2 and all this, because the balance is messed up. So this is the nature balance, and you can see here the white numbers, the yellow numbers. It's coming out, and then the planet has a mechanism to get it back. Like the tree over there, they take 120 units in, and the microbes in the soil, they give like 60 units, and the tree themselves gives 60 units back. 60 plus 60 minus 120, balance. Good. Ocean over there gets 90 in, 90 out due to respiration. Good, balance. So what we did as humans, there were a bunch of things over here, and then we managed to sort of get them out and then turn them through our biorefinery and our jet fuel and our asphalt and plastic and this jacket. We got this carbon from there up to the air, which we made 9 units. So we humans made 9 units and then say, hey, nature, take care of it. We made this mess. You take care of it. So the trees came in and say, okay, human, I'm going to help you. I'm going to take 3 units. And you keep hearing we plant trees, right? You keep hearing we plant trees in Amazonia and all this. So they can do 3 units. And then the ocean can say, okay, you made a mess. I'm going to take 2 units out of your hand. So we inject CO2 into the ocean and all this, 2 units. Together, they help us with 5 units. How much did we make? 9. We end up with 4 units on our hand. It's like if you take a best medicine, it's good for you, you get well. If you take too much of the best medicine, you're gonna die, right? You agree? Your doctor said don't take too much. So here we have too much, that's the problem, simple. So I want everybody to get on the same page since we all love our planet and we wanna make it better, that's the mess we have. So if you make a mess in your home, what would you do next? Come on, what do? You clean it, right? You go get a vacuum cleaner and you come clean the floor. You just made a mess. So if we made a mess over there on the air, what would you do? Clean it up. Thank you, George. We clean it up. So we thought in Arizona State University, for the first time in the world, my colleague Klaus and his team came up with a way to let's vacuum clean the air. I mean, analogy. So we started cleaning the air. We made this mechanical tree, which looks like a tower. We call it a tree, so accept as a tree for now. And then we hope at some point we will have in our desert, we have a lot of land, we will have a forest of mechanical tree. One mechanical tree works 1,000 times a tree. So we can be faster cleaning, and we don't have to plant as much anyway. So this is the first time, and it was on the news, it was a big deal and so forth. So that's a success. And maybe we can clean up in Arizona, and somebody in Houston makes, emission, because air moves. So we can clean here, then make emission over there. So that concept in nature, in nature, it works, but then you have to get those CO2s that Klaus collects with his team to do something with it. Otherwise, these are like huge tanks of CO2 that can be football stadium, needs football stadium to store for 1 day of collection or whatever. So then my team come in, and we get the CO2 and we convert them to biomass. That's we feed them into our pool of algae. We grow algae there, and then the CO2 become mass, the volume reduced by orders of magnitude. So now I have a bunch of biomass in my hand. But imagine if this algae, which is a creature, like is living being, right? Algae is living, like us, it lives. So while it's living is okay, but I don't have enough space in my pool, like the swimming pool this size, to keep them alive, because they keep breathing and become more and more and more. So I have to collect them, because if they die, like us, if we die, we decay, right? So if they die, they decay, they give the CO2 back to the air. So before they die, I collect them, turn them to a very stable carbon, which is that back there. It's not diamond. Why is a carbon that has more value than original? So we make that carbon, and I'm gonna get you, give me a few more seconds, I'll get you to the rubber. So this carbon, called functional carbon, can be made from different sources. I'm just showing you that you can actually turn CO2 to something through this method. So here is the carbon that we talk about. And we know CO2. I just showed you my beautiful carbon. I told you about the beautiful diamond, right? But carbon comes in different format and different shape. Think of it, what you're breathing right now. Breathe. Breathe deep. Breathe deep. What did you breathe in? What did you took in? Oxygen. George thinks he got oxygen. Hydrogen you got. What else you guys got? Ask your lung. What did you got? Yes, we got oxygen, hopefully, so we survive. We got some nitrogen, maybe hydrogen and all this. The bunch of other stuff in the air that may not even smell, and they're cute. And these are some of the stuff that as you walk outside, or even here, we did some sampling in different rooms. So I don't know about this, but many rooms also have some that you don't even expect. So there are some other carbon-carrying elements. These are all carbon. You know, right? This ring that you see, it has 6 carbon already in it. So there's so many different forms of carbon. But we always talk about CO2. Hey, CO2, you are the devil. You are making the climate change. But because all of these could contribute to climate change, the greenhouse gas in different format. Like imagine, 1 methane, which is CH4, 1 methane, how much worse than the CO2, you think? 21 times. So if you have 1 methane floating right here, and 1 CO2 floating, how many greenhouse gas you have right now? 22, because you have 1 CO2 and 21 CO2 equivalent. That's how we report. So what you hear in the report say CO2, 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 because we convert everything else and we report in CO2. So these are some of your friends there that you don't want in your lung, and they could actually contribute to greenhouse gas. So why I'm telling you this, I'm actually an engineer like you. I work in pavement, I work in material, and so why I'm talking about these things? Because it comes back to our roads and pavement, and it comes to the rubber, that actually we can improve our road by reducing mass loss by reducing emission. You may say, well, mass loss is like 0.001%. I would say no, because it's the road sitting out there 10, 15 years and so forth. So if we can actually stop the loss of those molecules, some of this coming out of that guy there, then we can do better. And that's where the rubber comes into play. It can actually reduce mass loss, keep your road in a better condition. So this brings me to the rubber applications, where we actually do dry mixing. That dry mixing rubber, or RAR-X, or equivalent, or ultra smart mix, or any other type of dry mix rubber, it itself could help us grab some of these molecules. It could make our road, yes, less noisy, less better routing, less yes to everything you talked last few days, and reduce emission. So I know you know this. So you reduce temperature, you mix it easier, it's pre-activated and all those. It can bring some of these advantages. This paper came out a few years back, and of course it's controversial. Some of us in the room, we don't want to believe it, and we argue against it. But even if it's not as harsh as they said, we know there is some. Have you ever got out of your car in the summer in Portugal and smell the road? I do smell it in Arizona. When you get out of the car, the parking lot smells. If you hear a smell, where do you think that the smell came? They didn't put perfume there. That smell is the molecule that was in the road. It's coming out, it goes to your nose, you hear it. So I know some molecules come out. How important, maybe not as significant as this guy said, but forget about what they said. We want our road last longer, isn't it? So the molecule we put in there, it better stay there. We don't want it to leave and come to my nose, it belongs there. So let's stop that. So what we did in my group, we actually come up with a simple, very simple, it's not a rocket science, adsorbent to keep what belongs to asphalt in asphalt. And if I don't lose some of those molecules, I'm way better off. I'll show you how a little bit, but you can read some of our papers showing how significant it is if you keep that smelly molecules right there. Don't let it come out, how significant it is. Weight-wise, I know we are engineers, we tend to measure things, measure like weight, say 1 gram, 2 gram, 3 gram. Here we're talking about molecules. Your scale cannot capture the weight. So you may say, oh, it's small. But that small thing, it will actually impact your road big time. And I'll show you how. So when you actually lose mass, when you have an asphalt road and you lose molecules, tiny, tiny molecules, what do you think it happens? Those molecules are gone, they're not important? Nobody care about them? Do we care? So why would we let them go? So we may say, and many of my colleagues, actually, believe me, I talked to many of my colleagues, they say, well, Ellie, this is just like very small amounts, and it's, over years, who care about them? I'll show you, we should care about them. So we talk about colloidal stability, and just in a simple term, I don't want to go too much into chemistry, which my group does a lot of chemistry, but what is colloidal stability? It means we are in balance. So if asphalt is made of a lot of molecules, right? You agree? Asphalt is black. You look at it, it's black, but it actually has a lot of molecules, millions of molecules. These molecules are in balance. If you take some of them out, the other one dominates. It's like an enemy, it is like a fight. When you go to war, if the different countries, actually different countries in geopolitical situation, if they are balanced, nobody attack each other. But if one gets like strong, maybe actually eats the other part. So here we don't want to lose the balance. If you lose some molecule, you lose the balance we call colloidal stability loss. And here we showed, okay, even if we do care about air quality, emission, climate, and all this, but even if we put that aside and we're a bunch of asphalt lovers, still we care about colloidal stability because it can make our road last longer. So here we show colloidal stability actually connects with the molecules we lost. And I'll show you a little bit of chemistry. I'm not going to go too much through it, promise. So here is what you have in asphalt. You see all the black molecules, but actually there are different molecules. Up there you can see the middle one, the big black one, that's one category of molecules. Then you have those green ones that are surrounding the black ones. That is in a stable situation. The green one don't let the many black guys in the middle to come together and collapse. Here you can see this is a balanced version. If you take the tiny green one out, you're gonna get a stack of this. So all those big molecules will collapse and make a big aggregate. When we say, oh, our asphalt is brittle, our asphalt lost its flexibility, global raw parameter is no good anymore, it's not. Why? Because the asphalt is changing. So we measure all these awesome tests to check for this. And we see it's gone, and we could stop it. We could stop it. And it's not actually very costly. And I love rubber. That's why I came to talk to in this conference, because rubber could be actually a solution. With a little bit of tweak, it could be a solution. So let's stop losing those green molecules to keep our road longer. I want to show you this picture so you get a sense of what is in your asphalt. I know everybody has dealt with asphalt of different sorts, right? Whether it's PG 6422 or as Arizona's or Portugal, it's all asphalt. We all call it bitumen, binder, asphalt, same thing, right? That's asphalt. Asphalt made out of these components. So you see it black, but if you actually look deep and separate components, it's like a soup. You know, when you make a soup, you have different stuff in it, right? Agree? It's a soup. We call it the soup. But soup has stuff in it. Here are the stuff in your asphalt. These are the 4 stuff in asphalt. And your brand new asphalt, this stuff are imbalanced. This is like one troop, one troop, one troop, one troop. As it ages, this troop, they lose their number. Look, these guys, poor guys, end up with 2. This one is big. So now this is going to kill that one, because now the armies are not in balance. So we want to keep the armies in balance in asphalt so they don't attack each other and kill each other. And of course, all these fancy tests, I'm going to show you a little bit of fancy tests, but fancy tests are all the same thing to tell us how material changed, how things got aged. Like we look at ourselves, we can say like, oh, I got wrinkle here, I'm getting aged. Asphalt the same. You look at it, you can say it's aged or not. So this is an aged asphalt. Brand new, 0-hour aging, 400 hours of aging. Look at it. You can say by time things are changing. So whether it's under microscope or using the GSR, DSR, MSCR, all these tests telling us the same thing. And that's the thickness of the film around your aggregate. You cover your aggregate with the bitumen, with asphalt. That's the thickness of the film. See, we start from 600 nanometer in that sense. After aging, the thickness is gone. It's going down to 150 nanometer. Of course, it's nanometer. You may say, well, it's nanometer. Who cares about nanometer? Well, that's doing the trick. So the stiffness, this is what we measure. With all our rheology tests, DSR, MSCR, that's what we measure. We measure mechanics. We apply load. The black there is only, the black line is 20 hours aged. You see the red and green is 100 or 50, 100 hours. It gets shifts, right? It shifts up because it's stiffer. And this test, nano indentation, very fancy test, very expensive test. It says the same thing. Basically, you put a film of bitumen and you apply the load, you poke it like this, and you measure how stiff it is. It is stiffer. And this one. Can you say which one is aged? Can anyone say which one is aged? Come on, my grandma can say that. Yeah, thank you, George. You can see its age. So all the fancy tests I'm showing you is a different way of telling you how aged it is and quantify it. So like this test, which the equipment costs $1.5 million, I got this test done, and it tells you how aged the sample is. This one, it says the surface, and this is a more aged one. So yeah, the chemistry changed, the molecules change, and all this. So we can quantify the extent of aging. And of course, this one is an atomic force microscopy. So with the atomic force microscopy, I can say which molecule has changed and how it has changed. Is it oxygen? Is it broken chain breakage or whatnot? So these are very good tests, but ultimately come back to the same story. It tells you that colloidal stability that you had is lost. And maybe we could have stopped it, and we could actually add few years to our roads. So this is what we actually emphasize a lot on this paper, and then it brings me back to, so how I'm gonna stop it? I showed you one aspect, which was functional carbon, can stop it, but I can't just add my functional carbon and spray it like a salt, right, on the asphalt. How can I introduce this functional adsorbent into the asphalt? We actually use rubber. So this one shows if you get that functional carbon onto the road. The functional carbon I showed you, it has a lot of arms. How many arms do I have? Do you see? Can you count? I have 2 arms, right? So if there's something grabbing here, I can grab one here and I can grab one there, right? Well, imagine if I had 7 arms. I could grab more stuff, right? So that's simply what we have done. We add functional carbon, which is many arms added to a core of a carbon. It has 7 arms, actually. So this one, with the 7 arms, over there, each of those are the arms of the carbon we made. Each one can grab many molecules, not just one. It can grab many molecules. So that one up there is the functional carbon, and this can block molecules from running away because it has more arms and it's sitting inside asphalt. So as the molecule goes up, it grabs it, it keeps it, and grabs it, it keeps it. So as it keeps the molecule, it delays mass loss, and we measured 70% reduction in loss. It's not 100, but it can reduce 70%. And we published that paper here. And this one here basically shows you how it does it. When molecules want to leave, they have to move. Even though we think asphalt, when we are done, we compact it, they stay there, and they feel good, they sleep, they're not sleeping. They actually move all the time. So even during the service life, they can move up and leave or move around and all those. So this is how the functional carbon blocks the movement. It doesn't let them easily move away and run away. And that's the arm. So I said, I have 2 arms, right? So if I have like an Iron Man arm or like a Spider-Man arm, maybe different. So I said, let's change the arm, see how it works. Here is 1 arm, this is 1 arm. This is just a modeling for 2 arms, and we saw significant difference what type of arm you use. So we did, this is like 7 years of work. So we did a lot of study to figure out what and how to optimize it and all this to make biofunctional carbon. These are the arms and energy and all this, but I skip those. So ultimately, if you put that Superman inside the asphalt, it has many arms. A simple fact. It just keeps the molecule, and it's designed, these arms are designed for the molecules we know is in asphalt, not for a random molecule. So those arms actually can reduce mass loss, reduce the oxygen diffusion, free radicals. They don't diffuse as fast because it has these arms that blocks it, and reduce aging. And this is what we can actually show. So my folks in engineering, in road authority, they told me, okay, all the fancy thing you showed us, prove that it works in actual Arizona asphalt. This is actual Arizona asphalt. Black is Arizona's asphalt. This one is carbonyl index, which is a sign of oxidation aging. When our asphalt has a lot of carbon, right, 70, 80% carbon, oxygen comes in, COO become a sign of oxidation aging. Here we have COO bond, and you can see when we have the functional carbon is lower. And there we have mechanical performance. You can see crossover modulus, which is a sign, an analogy or indicator of how brittle, how stiff it gets, how much it loses the viscous versus elastic performance. It shifts. The lower the shift, the lower it goes, it's worse. So the black is really bad. It's getting really, really bad after 200 hours. The green, it doesn't get as bad, and we feel it's getting actually to plateau because it blocks it and it doesn't let more diffusion. And that's where we added to rubber. We can't just dump it in the asphalt because these are particles, they can't just, disperse, they cannot disperse and all. So we introduced this into the rubber. We made an activated rubber, which has all these arms. Yeah, the first day I asked a question from George, he was answering that, don't worry about what's inside. It's inside, and this is RAR, so that's accept as is, right? So I'm talking about what is outside now. So we made activated rubber with many arms outside of it. And the arms are standing like this, not like this. So we designed it to be 7 arms around it, around each carbon. And this is what we made. Thanks to my friend Doug, we made a bunch of this stuff, which is rubber activated by biomaterial, made it bioactivated rubber. So here, I introduce you to bioactivated rubber, which has a little bit maybe more than regular activation because now you added an absorption mechanism to it. And here is some of the results that we can, yes, I made it with algae in Arizona and all this. We are mecca of producing algae because we have 320 days of sun, and it's a very ideal situation. But you don't have to just use algae. Here are a bunch of other biomass. You heard about California fire, right? California wildfire and forest management, and also there is a lot of interest to manage forests by turning biomass into added value product. They asked me, I got a project from US Department of Agriculture to see if that works on forest residue. These are forest residue. And we can make it maybe different than algae, but we can make functional carbon. And I put a red box there so you can see actually how much carbon we have in this, guys. We have 77, 61, see that row? Each scenario of biomass gives us that much carbon. These are fixed carbon and can be considered as biocarbon. You're all familiar with biogenic carbon. It's not the carbon that comes from under the earth. It's coming from the air, right? So plant, trees, turn CO2 with photosynthesis into mass. Mass become this carbon. This considered carbon neutral. So we call it biocarbon, which could possibly get you carbon negativity at some point or neutral for the product if we use it. So for the performance, I just want to show you the aging one. This is the regular PG. Just look, don't worry about the whole table, just this row. But all rows the same trend. But look at this. We have 114. Every single addition end up with a reduction in aging. So this is not like one scenario and say, oh, only work for this. No, it actually works for different scenarios. Very cheap source of biomass to very expensive biomass, they all work better than the control because they have the capacity to grab those molecules I told you. So this here, it proves that this can work. But then come back to your sense of the test that we do. Ideal city, you heard the speaker talking about. Of course, if we introduce this guy into the rubber and this rubber become activated rubber and then we dump it into asphalt, I want performance, right? Here is performance. We run ideal city, and as soon as we measure the ideal city city index, we get 134 for just addition of this tiny adsorbent rubber, the new rubber, 80 with the regular activated rubber. Both are activated. You know, activated rubber is good. I love it. It works. Dry process. We change the surface of that, and it become 134. How that works? Because rubber is rubber. You have this rubber particle look like this. Inside of it, you put the magic oil, bitumen, whatever, and you put hydrated lime outside and all this. This is ready. I'm going to come and cover the surface to become functionalized. It's not a coating, but anyway, at the end, you see the same look, right? This is the look. Same look. But those arms, I told you, you can see it with your naked eyes. Right? You can see, oh, where is the arm? Where is the arm? You can see it. The arms are there. How do I prove the arms are there? With this. Same activated rubber, that is out there, we did it with this bioactivation, we got to 134. I know it happens because on the chemistry side, I knew it happened, but I want to show you that it happens. So I did the ideal CT. And then we did the MSCR. I know ideal CT indicator of crack, so okay, good cracking, good cracking. What about permanent deformation? What about rotting? The car comes and go. The road between every car has to bounce back, right? That's why we measure rotting. So here the car goes, then the road has the elasticity to come back. Otherwise we get this sagging. So here we run the multiple stress creep recovery test. We measure the strain residue. If you're not familiar with the test, it's basically a repeated cycle of loading. We keep loaded, unloaded, loaded, and we give a rest period between each loading. So loaded, wait, unloaded, wait, load, unload, load, unload, 10 cycle. We measure how much strain accumulate in that material. If it's 100% elastic, like a rubber band, you do 1, 2, 3, 4, 5, 6, doesn't matter. You go back, right? You agree? Asphalt is not 100% elastic, so it keeps a little bit accumulation. But we don't want too much accumulation because it's going to get rotting. That's why we run this test, and here is what we see with the reacted and activated and the bioactivated. That just has more arms than that. They're both activated. So you can actually, these arms, because they are stretched out, they interact with the asphalt surrounding it. It will keep the matrix more elasticity. It gives more elasticity. This is how it looks. So inside of the rubber, when you swirl it with asphalt, when you swirl it with oil, with other things, pre-swirl it, pre-treated, and so it doesn't suck the oil later. I know all the concept behind it, but let's say we got this pre-treated, ready-to-go rubber. It's all inside, right? It go inside. Those are the oil inside. What we add the oil that also stretch outside. So it has tiny bit of connection outside, and that's how it connects with the rest of asphalt. Remember I told you asphalt is made of those 4 elements? Those 4 elements, they have different affinity. They don't all interact the same way. If you understand the 4 elements of the soup, like we have carrot and potato and chicken and water, they're not the same. So if you want to interact with each element, you have to optimize it for that element to interact. These are molecules of those 4 that I showed you. Each one of them looks different. Their color even is different. Those are ingredients of your asphalt. So to make the best interaction between your activated rubber and the surrounding, which is bitumen, or in case of my Taiwan friends, resin, doesn't matter. That rubber has to see around it and interact with it. It's not isolated. So this is what those interaction is working. And then one test that we did to also measure the bonding. I know you're familiar with TSR, for instance. We do TSR, we do bitumen bond test, we pull it and see how good it sticks together. It's also not a magic test. But how do you know this rubber that I made with this bioactivated, this rubber I made with no bioactivation, and this regular rubber? How does this interact with the bitumen? Like here is bitumen. How does this interact? I can ask the rubber, how do you like the bitumen? Do you like the bitumen? That's one way, but he can't respond. So how do I know this likes my asphalt? You heard few tests at least. We do separation tests, right? We do separation tests and see how they like. And my friend was saying that the terminal blend guys are worried about segregation, separation. That means the rubber maybe doesn't like as much the asphalt. You want to separate. It's like when you mix vinegar and olive oil. You shake it, it's good. You put it aside, it's separate. But then they don't like to be with each other. I mean, they're telling you. So how do I get my rubber to love my asphalt? I need a coupling agent. I need someone in the middle to grab the rubber, because rubber, just by nature, is not asphalt. So as much as we work to make it like love each other, please, love each other, they're not compatible. So what we do, we have to help them. We do a coupling agent. Like I get a friend here, I love this friend, and George loved this friend. So now we love each other because we love this friend. That's called coupling agent. So we add a coupling agent here, and that's the arm designed to be the coupling agent. And we measure it here. Look, those red lines there are the coupling agent. If you don't add the coupling agent, you push the droplet there, it moves easier. You add the coupling agent, it doesn't move as easy. So we add the coupling agent there, and we measured it. So we saw a significant difference in this test. If you're interested, read this paper. It basically tells you how can you measure binding of things, like tiny things, that they cannot talk to you. So how they like each other surrounding. You can do separation index, or you can actually quantify how they like each other. I'm just showing you this test to tell you if you make a coupling agent, you can actually make a difference. This is bio-treated. That one is organo-silent treated. Different treatment. I'm not saying which one is good or bad. Different treatment. Different coupling agent. Different love. If we put a friend here that we both really love, then me and George will be more connected. If you put a friend there where we don't care as much, maybe we're not as much connected. And this is the coupling agent. So just tell me by look. You don't need to know chemistry, and this is quantum chemistry. You don't need to know quantum chemistry to tell me which one of these you think love each other better. I have two. This is me and George. This is me and George. This is the friend. Do you think this is a better connection or that one? Which one they love each other better? Yeah? Yeah? Good. So you can actually say from this, the organic, they like each other, they like. So the one in bottom actually, it does better. So here we measured it and we saw actually different friends, they can be distinguished in their love. And we tested it. So all this came back to say, what can I do? You may say, okay, you told me all this, how can I do it? I'm actually practitioner, I want to do it. Tell me the secret. Here is the secret. You can make your rubber love your asphalt by changing the surface of it. Let George and Doug activate and do the activation, and then we come make sure that the surface love asphalt. This is the love. You can use microbes. You can use bio-activation on the surface, because bio is organic. They love each other. If you can actually use the right material, you can do it. In one scenario, we use bio-oil. In one scenario, we use microbial treatment, both published in this paper. You can check it out. Actually, the microbe does magic. But I'm not going to tell you go use microbe. I know most of my friends don't like to touch microbe. They even worry about the spread and all this. These are not pathogenic. But the way that we treat them, we treat the rubber with microbe was amazing, how it becomes asphalt loving, and it works so well. So we use the microbes as our bio-inspiration. I told you I learned from nature. I learned from microbes, went back and activated the rubber. Now we have the bio-activated rubber, which it doesn't use microbe, I use bio-oil, biomass. And that's, by the way, separation. So those of you who love to look at separation index, that's the separation index that goes down to 4 from 35. And the surface. If you look at the rubber I showed you, it's all black. You touch it, it feels the same. This is the surface under microscope. This is the regular one, and the last one is the activated one. So the surface looks different under microscope, and this is the chemistry, how it works out. Some about devulcanization, partial devulcanization, which is beyond this talk, but I will be happy to talk about this process, how microbe devulcanize the surface of rubber, and how we learn from that to bring it back to make it simple with the bio-oil, and publish it there. So this activation, these are my microbes. So this is the family of microbes we use, and we identify these two microbes, Cordonia and Narcadia. These are our bio-inspiration. We learn from, especially in Cordonia, to mimic the performance of Cordonia, and then we made our bio-treated rubber, which is actually made with bio-oil. No microbe at all. So this this is for the low temperature cracking, for instance. Look at CR16. You can see the stiffness and the M value. M value actually gets a very good low temperature performance. We also did recovery. This study is still ongoing, but we can actually make it interact better. And just to bring you back all to carbon, remember I told you these are they are biogenic. Biogenic carbon give you carbon negative of -45 there. So if you want to count as negative, right there, you have -45 kilogram CO2. You can use it to add to other carbon, and this made it to this journal where we talk about carbon management. Can we use biomass as a means of carbon management in our roads? And just to wrap up on this, I come back with environmental stressor. I told you if you is in the closet, it may not mass loss, it may not go through all this stress. Environmental stressors are really important. Whether you cover it from moisture and sun, you will still have humidity in there. So humidity in Florida is very different from Arizona. The same method, same exact rubber, same everything may work in Arizona, may not work in Florida, just because the humidity actually changed the whole dynamics of the process. And I think we're running out of time. We're running out of time, but any of you would like to talk about the role of humidity? Me and Dr. Prass, sorry, I use all your time. We can tell you about all the humidity and the magic of humidity that can change the. We are working with a group in France. Different humidity, different impact on the performance. But we typically don't test it. We don't even have a test in our specification. We dump it in water, do TSR and all those things. We don't do humidity. And humidity can have non-linear effect on our performance. So with that, I leave you with this. Read this paper on carbon management. Let's do it more green.
Thank you. Thank you. You want to take up questions?
Thank you so
If you want to take up.
Thank you so much. Please, it's important that when you leave, go at the end and make sure you tell us if you are going and how many people of your group is going in the tour tomorrow, okay? Because they need to know how much food to prepare for you near the beach.
Okay. So we can take up questions later during the discussion, okay? Thank you so much, Dr. Elam Fini. And this comes to the end of the session, 7. We'll see you back at 12 p.m. for the next session. Thank you.
Yes, so that's right. We had the students mobilized to the sites, so they were active. Yes, so we've seen this trend in other tests. So what this is telling me though is
É, sabes porque é que estou? Estás a ver? Não, não.
Está na escuta.
All right, we should get started. We're only an hour behind. Is Rajmi here? Rajmi, first speaker on this session? Zankovic, you're here, okay. I just want to make sure, and then Gopa Kumar. Gopa Kumar is here. Oh, okay, all right. Mr. Zankovic, I think we can start with you because the first speaker is not here. Would that be okay? All right. So, so we have a couple of speakers and a keynote in this session. It's my pleasure again to moderate this morning's session just before lunch. The first speaker is Zankovic. We're talking about using textile fiber derived from the end-of-life tires. So that should be very interesting. And you can introduce yourself, who you are, and we can get started.
Yes, I am ready.
Perfect. Let's just do it.
Ladies and gentlemen, good afternoon. My name is Vitaly Zankovic. I represent Polish tire recycling company Recycle. And I want to say what, together with my colleagues from Poland, we have listened to numerous insightful presentations during 2 days and gaining valuable information about rubberized asphalt and asphalt rubber, of course. And we would like to share some of our findings, which we hope will be beneficial for you as well. Our presentation about synergy, which we have if we use together ALT fibers from used tires, of course, in different asphalt mixers. Here will be information about dry, crump rubber, modified, gap-graded asphalt mixers. Like you know, the current level of motorization worldwide has reached approximately 2 billion vehicles and increasing 30-40 million units annually. For instance, for example, in Poland, the annual growth exceeds 500,000 and every year and continues to rise. Such traffic loads, of course, necessitate continuous improvement of road networks and especially asphalt pavements. Increasingly, stringent requirements are imposed on asphalt mixers and their key component, it's bitumen. The most common method for enhancing bitumen properties is modification with thermoplastic elastomers. While these modified mixtures offer advantages such, for example, improved crack resistance, fatigue resistance, or rutting resistance, they also present drawbacks and notably higher cost, for example, and ambiguous environmental impacts. There is also concern that maybe we have in polymer modification, maybe we have been reached. We may have been reached, for example. And we have phase inversion, for example, and other difficulties with high content of polymers in modified bitumen. This conference focuses on effective practical solution for durable asphalt pavements under current load condition, specifically for use of rubber recycled tires. Rubber for these tires contains numerous very valuable components for modification, such as rubbers, and antioxidants and active fillers, for example, and while this cannot be purchased separately for reasonable money, they are readily available in used tires, which are often incinerated. In Europe, near 40% of ALTs is incinerating. Also, incineration has its merits, of course, but more efficient alternatives exist. For many years, recycled tire rubber has been used to modify bitumen and asphalt mixtures. Wet modification, as you know, technologies are more widely adopted due to their reliability and applicability to a broader range of mixtures, and by their costly and have a higher environmental impact. Dry modification technologies are simple, cheaper, and environmentally friendly, but less reliable to depend on mixer type and design accuracy. Therefore, hybrid and semi-wet, for example, methods are being developed along with technologies like reactivating and devulcanizing tire rubber to improve homogeneity and efficiency, reducing reliance on primary polymers such as SBS, for example. We have some advantages, but we have some disadvantages. Synthetic fiber, for example, obtained from end-of-life tires, represent an underutilized resource that can be enhanced rubberized asphalt technologies while addressing waste disposal issues. Modern tire textile cords are made from high-strength fiber, for example, polyester, polyamide, aramid, and viscose, which can serve as structuring and reinforcing components in asphalt mixture. These fibers are temperature and chemically resistant, polymer coated, and surface active, facilitating optimal interaction with bitumen. The rubber granulates production process yields fiber mixture with lengths of single fibers up to 1-2 centimeters, often containing micronized rubber, but which can be adjusted if we need. The composition of rubber powder can be tailored, for example, to include specific proportion from truck or passenger tires. Of course, we need to have some content of passenger tires because we need to have textile. In Poland, for example, such fibers are produced industrially in our company as pellets and used as stabilizers in SMA and other upgraded asphalt mixes. Beyond binder stabilization, these additives significantly enhance rotting resistance, for example, fatigue life and low temperature crack resistance and water resistance. These results are consistent with global studies. There are many studies in the world about this textile fiber for performance of asphalt mixes. And the technology has reached in Poland for serial production, and the pellets blend seamlessly with other asphalt mixer component into the asphalt mixer, ensuring homogeneous fiber distribution. These additives are nearly carbon neutral and considering their production process emissions and are used in rows for all categories. The objective of our research was to assess the impact of synthetic fiber and rubber from ALT on the properties of bitumen mastics, a key structural element in upgraded asphalt mixes. The bitumen to mineral filler ratio was constant, like 1 to 1.8, and the fiber and rubber content in the mastic reached up to 25% by bitumen weight. Cleaner synthetic fiber and rubber powder with short fiber were used, and mixing was performed at 175 degree in 3 stages to simulate standard SMA production and transport. Mastic properties were evaluated using next testing methods, multiple stress creep recovery at 60 degree and dynamic stereometry at 80 and 10 degree, and rotational viscometry at 175 degree. Results indicate a high level of synergy if we use combined of rubber and fiber together, for example, comparing composition 2 and 3, where we have, for example, content of rubber 8% and content of together rubber with fiber 7.5%. You can to see different results, and results where we have fiber and rubber together are better. The difference is in non-recoverable creep compliance and elastic properties is 4.4 and 1.4 times. And notably, elastic recovery reaches 90% with combined fiber and rubber content, and 8%. And all results demonstrate the effectiveness of fiber-rubber mixtures in improving mastic properties, including rotting resistance, fatigue life, and technological properties such as binder drainage and workability. Similar conclusion apply to rheological properties from DSR test at 80 degree. Rotting resistance increase with fiber or total fiber rubber content, of course, and the phase angle is 50-60 degree with more than 7% of combined rubber fiber content. High temperature properties match those of PMB modified bitumen mastics. At 10 degree, fatigue resistance improvement is less pronounced, but still better than conventional bitumen 50-70, bitumen mastic on bitumen 50-70, and however, with more than 30% of combined rubber fiber content, fatigue resistance drops to levels of the conventional bitumen, not reaching modified bitumen performance. But we think this is an area for further research. Perhaps this issue can be resolved by simply adjusting the properties of the rubber. Dynamic viscosity increases, of course, at temperature 175 degree, addressing binder drainage and in gap-graded mixtures, but combining fiber and rubber content more than 7-8% may reduce workability, of course, in standard temperature. For highly gap-graded mixtures, higher content may be acceptable. Modified bitumen mastics often lack sufficient viscosity, which is typically resolved by addition cellulose, for example, but cellulose further increasing costs. Now, if we use synthetic fiber together with rubber or only synthetic fiber, no need cellulose, and we have little better properties. Fiber and rubber, and at more than greater than 8-10% of bitumen weight, ensure adequate binder drainage properties and further optimization of possible with higher quality rubber. For example, we can do next research with different properties of rubber. For example, it can be reactivated rubber or devulcanized rubber, and I think we can to achieve some more interesting results. A preliminary assessment of synergy was conducted by comparing mastics with only rubber and to those with equal fiber and rubber content. At identical dynamic viscosity, for example, up to 7-9% of mastic weight, a significant synergic effect is observed for all properties indicators. For example, for highest energy, 5 or 10 times, was noted for non-recoverable creep compliance, and other properties indicators showed synergy levels to more than 2 times. And the lowest was for the shear stability index at maximum rubber fiber mixture saturation of mastic. The effect on the fatigue index is minor, of course, but rubber slightly outperforms a fiber, and fiber excels an elastic recovery at 60 degrees, especially with we have content more than 7.5%. And both fiber and rubber similarly affect the dynamic viscosity near 2 times synergy. And achieving required technological property is feasible with up to 7-9% rubber fiber mixture in bitumen mastic. Higher saturation may reduce workability, necessitating higher mixing temperatures and compaction effort. Experiments with SMA mixes, SMA8 mixes confirm the synergic effect, and for example, SMA8 with 0.5% of rubber and 0.5% of fiber outperforms mixtures with only 1% of rubber or only 1% of fiber. Together, rubber and fiber have better results, like in rutting depth, structural strength, and binder drainage of asphalt mixes. Research results demonstrate the potential. Of course, this is our first big research in this field, and of course, results demonstrate potential for synergy from the combined use of ALT synthetic fiber and rubber. Their joint application can enhance the reliability and durability of rubber modified asphalt mixtures while reducing rubber and/or bitumen consumption. Combined system for dry, semi-dry, or hybrid modification methods can be developed based on such fiber. This fiber can serve as effective structuring agent for ALT rubber-based granular additives, for example, ensuring high homogenization in asphalt mixers. Further research is needed to optimize rubber properties and modification methods to maximize synergy of both mastic and asphalt mixtures levels. It's enough.
Thank you very much. I think we can take maybe a question or two from the audience. Very interesting work. No questions? I have a question for you. Why we don't see more of this rubber fiber systems being implemented? I mean, why do you think, is it related issues, the challenges of the fiber distribution in the mix? Or is there any, challenges for such systems to be more implemented out there by agencies?
Like I said, we have fibers with length of 1-2 centimeters. Of course, we have not macrostructural reinforcement, of course, like with different long fibers and high-strength fibers, but we have microstructural reinforcement, and we can change properties of mastic in our structure of asphalt mixes. For example, like SMA or in different gap-graded asphalt mixes. But I think, of course, where is film of binder is very high. But if we have some different asphalt mixes with low film of binder, like AC mixes, we need to have better properties of rubber in our additive to have good interaction with bitumen and good workability and other. But I think the most important effect from this textile, it's a microstructural reinforcement of mastic.
Well, thank you. Maybe later on at the end of the day, I know Arizona, George, you used those in the early days, a combination, but we kind of shied away over the years from that. Well, thank you very much.
Thank you.
Presentation. Okay, we have another presentation here. Gopal Kumar and the co-authors, yes. you know how to get to your presentation, or how? There you go.
So good afternoon to everyone present here. My name is Neetu Gopakumar, and today I will be presenting my research on rubber plastic conglomerates as sustainable aggregates, assessment of asphalt interaction and swelling dynamics. So this is a research team. Firstly, I would like to thank my advisor, Professor Krishna Prapurna Biligiri, for his support throughout this research. And before I begin, I would also like to thank the organizing committee of this conference for providing me with this opportunity. Thank you so much. So starting with the presentation background, so this research is particularly focused on the subsurface layers of the pavement system, that is the base and sub-base layers of the pavement system. So as we know that the commonly used materials for this layers are the unbound granular base materials or the aggregate materials. Now the commonly used additives to this layer is the cement and asphalt, which we call as a cement treated base, and the asphalt treated base materials. Also there are research emerging on the use of recycled materials such as the recycled concrete aggregates, the tire derived aggregates, and the wrap material. So here we would like to investigate more into the use of tire-derived aggregates and waste plastic materials into the pavement subsurface layers. So as we all are aware that these are the materials that are waste materials that are very abundantly generated in huge amounts, and there is a need of recycling these two materials. So coming to the rubberized asphalt technology, there is, again, we are familiar with the wet process and the dry process. So this research is again focused on the dry process, wherein the rubber aggregates will be replacing the conventional aggregates. So again, as Dr. George Sousa rightly mentioned, that the wet process is good, but the dry process has to be pre-treated, so that we can incorporate it as aggregates. So in this direction, the waste plastic material was adopted as a pre-processing coating layer to the tire-derived aggregates. So as we can see, these are pictures that were captured at a local recycling plant in India. And these are the steps that were adopted from collecting the waste plastic materials to pre-processing them into pellet-sized materials. So again, use of the plastic materials into the asphalt matrix is not that straightforward, because there are huge variety of plastic materials and very different types of plastics, such as high density polyethylene, polypropylene, and the polyethylene terephthalate materials. So we will be investigating all of these into this composite material. So the major objective of this study was to assess the compatibility of this rubber plastic composite into using into the subsurface layers of the pavement system through a semi-dry process. Now coming to the methodology that we have adopted to prepare this composite. So we have utilized three different types of plastic material, where we prepared a plastic modified asphalt blend by the wet process, which we then coated with the tire derived aggregates using high shear method. So these are the pictures that we see on top, that we could prepare three different products with three different types of plastic coated rubber aggregates. So these are also the preliminary tests that were conducted on these products to assess the microscopic as well as macroscopic understanding of the swelling potential of these materials. So these are some of the images that of the products that we developed. So these are the two sizes of rubber materials, that is the 5 mesh and the 10 mesh size of the rubber that were developed. So, and this is the proportions of the materials that we have adopted in this study. So this product was then incorporated into the mixture through a mix design method, as well as to understand the swelling potential of each of these mixtures when the unprocessed rubber aggregate as well as a processed rubber aggregate were utilized. So the amount of the dosage of the products or the rubber material going into the mixture was about 10% of the fine aggregates. So we were able to check the swelling potential through two different stages. That is, first is the initial rebound that happened immediately after compaction, and second is the gradual or the progressive, the cumulative swelling that took place over a period of 24 hours. So each of these were recorded. So these are the results of the chemical characterization of the products that we developed. This plot shows the Fourier transform infrared spectroscopy of the absorbent bands that we could see for all the raw materials as well as the composite materials that were developed. So we can see here the three different products using the three different types of plastic, HDPE, PP as well as PET. So we can see that there are similar functional groups present, obviously, for the raw materials as well as the composites, as well as there were also some of the shift in the peaks that were observed in the composites. So that could actually confirm the presence of some interfacial bonds between the raw materials, such as the rubber and the plastic materials. And these are the results of the BET analysis that were conducted on the products. So this test was particularly done to understand the surface, pore surface volume, as well as the pore and overall pore volume, as well as the surface area of the pores. So this also was conducted on the untreated as well as the treated rubber materials, and we could clearly see that when there was a treatment of the rubber done, we could see a clear decrease in the pore volume as well as the pore surface area. And the plot below shows the isotherms that were plotted for both of these products. So we can see that the desorption and adsorption curves follow a trend of the mesopore type, so wherein the pore size range between about 2 to 50 mm size. And these are the results of the swell testing of the product. So as we already saw, the methodology that we adopted was based on a dial gauge that we set up on the samples to measure the swelling over a period of 24 hours. So here are the results that we can clearly see that after a period of 24 hours, the cumulated swell that was measured for the modified aggregates, especially modified with PET aggregates, HDPE, we could observe a huge reduction in swelling. That is the initial rebound. We could observe about 65 to 70% of reduction in swelling, whereas the cumulative progressive swelling in about 24 hours, we could see about 30 to 40% reduction in swelling. So these are the results that we see here. And based on the tests that we have already seen, these are some of the conclusions that we could see. That based on the FTIR spectrum, we were able to observe enhanced interfacial adhesion or bonding between the raw materials as well as the composite materials. And especially in case of PET type of plastic and the rubber aggregates, there was a good amount of compatibility that we could see based on the functional groups. Again, coming to the BET method, BET analysis, we could see that MTDA is a modified tie-derived aggregate with PET type of plastic, had a slightly reduced pore volume and pore surface area. And based on the swelling test results, we could observe an immediate elastic rebound decreased by 70% and a cumulative swelling by about 30 to 50% reduction. So it is recommended that this study must further be conducted for performance analysis as well as environmental assessments. Thank you.
Thank you. Any questions for Gopal Kumar? Very quiet audience this morning, either hungry or trying to get going. Quick question, just clarification. Did you actually control, because of the waste plastics, they come from different grades, So did you control the content for your work, or how do you control the variability of that?
The content of the waste plastics?
Yeah.
Yes, so we have actually optimized the amount of waste plastic in the asphalt binder by all the advanced characterization methods of rheological test. Based on also viscosity test, we have optimized the amount of HDPE to be around 15% by weight of the asphalt binder, PET to be around 40% by weight of asphalt binder. And each of these products have different plastic contents as well.
Okay, thank you very much. Good work. Thank you.
Thank you, sir.
All right. I think we'll move on with the keynote for this morning. It's really my pleasure to introduce Professor Kelvin Wang, who is a director and professor of the Western Transportation Institute at Montana State University. I know Professor Kelvin, got to meet him last year. We actually inducted him into the Hall of Fame in our school back at Arizona State University. He's a graduate of ASU. And we are very proud of his accomplishments. If you just Google him, do the Google Scholar, you'll see how much publications and work that he has done in the field. So, Professor Kelvin, the floor is yours. Okay. You need help with that, or? Good to see you again.
Thank you.
First, I need to apologize. I did not use the standard format for the conference. But as you can see that this talk is in collaboration with George Wei. Many of you probably don't know my relationship with George. 35 years ago, I worked for George for a few years as a state employee, as a new engineer. Starting at Arizona DOT. The other thing you may not know is George's reputation started with his first statewide payment management system in the world. He started the work in the 70s through the 80s, and when I came to work for him, I helped him migrate the system from an IBM or AMDAL mainframe to a 486 PC in the early 90s. So that actually became my PhD dissertation. So George, I did have a PhD advisor at Arizona State University, but George actually acted as my practice advisor from ADOT. So that was an honor and a big association with George. Of course, he is known today as the asphalt rubber engineer on the world stage. But it's really an honor to be associated with George, the two Georges here, and also Arizona State University. We have quite a few people from ASU at this conference. I promise you that this presentation is not going to be very long, so I will not be the one that hold the lunch for you guys. So I'll go relatively quickly, so hopefully we have a few minutes for questions. I'm going to talk about something that's relevant to pavement engineering, but it's not exactly on asphalt rubber technology. But hopefully it can open some eyes regarding how this new development since 10 years ago would change people's lives and work, and also technology innovations in the coming years and decades. First of all, I would like to mention asphalt rubber a little bit because the AI techniques can be used for any kind of materials research today. The biggest I saw in recent year or two was for battery research for materials. Some of you are aware that solid-state batteries are coming along very strong in research, And in next year or two, there will be actually implementations of solid-state batteries that can run more than 500 miles or maybe 600-700 miles in one charge, 10 minutes charge, and it's safe. And it can run 1 million miles, still retain 95% of its capacity. So those things are coming along. It's going to change the industry and also people's lives. And I do believe AI is going to play a huge role in payment materials research as well. For those people that got to know AI in the last year or two, please, especially young people here, please learn how AI can help you in the future research, just because it can be very powerful in certain aspects. But this presentation focuses on the multifunction payment evaluation tools at highway speed. My work actually at Arizona DOT and for George 35 plus years ago gave me motivation to start a new research in addition to the payment optimization system we did together, how to collect data, how to analyze the data, how to use the data to benefit payment engineering. Payment evaluation has 4 major categories. One is surface distress. I always tell my students in classes that payment condition survey or distress survey is exact the same, not exact same, almost the same, as a doctor would look at you and say, what's wrong with you, right? So people who have problems, they would exhibit problems in the complexion and facial expression. That's how we payment engineers, we study payments. One thing we do is to look at the payment surface condition to see if it's telling you something's wrong, okay? The first thing is, cracking. When the payment is cracked, it's trying to tell you, say, hey, dude, I'm wrong. Something's wrong with me because I'm cracked. Please help. Of course, payment safety is another one. It's more like friction, texture, and payment structure, which is related to payment deflection, surface deflection, and then, of course, functional, which is longitudinal profiling. So among all those 4 categories, we have good solutions, mature solutions for longitudinal profiling, but on the other 3 categories, we are still struggling in some ways. This photo here was a collaboration that I did with Greenwood about 18 years ago for South Africa National Road Agency Limited. And so that was one of the first implementations of a deflection device along with payment surface survey with 3D laser imaging. AI in payment evaluation can be very, very powerful just because payment evaluation essentially is a classification problem. Okay, pattern recognition and classification. AI can also do cognition. What is a cognition? Like a baby can recognize the mother first, and then father, then siblings, without being taught. That's a very, very basic cognition. This kind of cognition is very, very difficult to be modeled mathematically. Even today, there's no mathematical solution. Can you produce a model? Can you imagine mathematically, even using a supercomputer, saying this model has cognition? No, nobody can do that, or nobody can demonstrate that even. But the deep learning does have a property of cognition, which is kind of very, very interesting, actually very surprising. Data is critical for any decision-making process. For payment engineering, there's no exception. If we do not have good data, accurate data, and timely data, we cannot really solve problems. So that's where I thought about this long and hard. After I finished working for George in the early 90s, I became a university assistant professor. I started working on data collection. And then, of course, PMS is the system that would manage the data, process the data, and produce results for payment decision-making process. I just mentioned it's very difficult, even today, to get a very high quality data in payment engineering. We know that civil engineering has many branches. Payment engineering is one of the babies. When you walk into any civil engineering program, especially the big programs, they always have a lot of people in geotech, a lot of people in structures, a lot of people in environmental, but we need to talk about payments. Some programs even don't have payments. Right now, most programs do, but we are not one of the big ones. A key reason, just my own personal experience, is that we do not have a sound science around our discipline. The reason we do not have very good sound science is because the quality of the data. We do not have quality of data. When you're talking about structures people, they have textbooks and textbooks with equations, with math models. They tell you that they really have a good solid science around it. In payment engineering, conceptually we do, but in practice, data quality causes all these kind of problems for us. I'm not going to show you this. This one requires the internet on a subscription, but I can tell you if you have New York Times subscription, this is 1 year old. This is a very striking story. There's a team of scientists and engineers. They actually modeled a fruit fly's brain, use deep learning. And that particular model can become real in a sense that it can react to smell and taste, okay? So there's an animation of this. I couldn't download it just because of copyright, but you have the subscription. Go to New York Times, October 2nd, almost exactly a year ago, they published this paper. What does that tell you is today, scientists and engineers are able to model a small animal like a fruit fly's brain. Okay, can you imagine what's going to happen in 5 years or 10 years? What happens if they can model a person's brain? And then what happens if they can model 1,000 PhDs' brain, different disciplines, and they can give you answers in a fraction of a second instead of days, years, and things like that. So it's coming to us. Potential AI in payment engineering, I mentioned earlier, we need timely information, accurate information, so that we can use the information to making decisions. And this is very, very important for long-lasting payment materials, asphalt rubber, and everything else we're working on in materials. Another item I would like to mention to you guys, I'm not an expert in this, but I think it's coming to us sooner or later. It's called artificial general intelligence. What is the AGI? It is a hypothetical form of artificial intelligence that possesses human-like cognitive abilities. Right now, including the version 5 of ChatGPT, essentially it is a huge database. Mostly would give you correct information with a certain level of reasoning. But can it innovate? Can it invent things? We're not at that stage yet. So by the time it can do that in the next 5 or 10 years, what we will have is essentially we have a human being's capabilities at a PhD level with thousands, maybe tens of thousands of them, helping solving problems. That's kind of interesting situation, but I cannot predict it's going to be 5 years or 10 years or maybe decades, but I'm sure it is coming to us. So it will exhibit common sense, reasoning, and problem-solving abilities, and it will have consciousness and self-awareness at some level. People even today, they said ChatGPT-5 and some other platforms may have certain features of this already, but I'm not certain about that. But in the future, is it coming? I'm pretty sure right now, because those hundreds of billions of dollars investment will do that. So For example, materials research, asphalt rubber in particular, we're still doing a lot of studies how to really doing a cocktail method, mixing fiber or different materials with rubber, and sometimes also with asphalt to improve the performance. What happens if AI comes into play? Instead of spending days, weeks, months to do those material testing, it's going to give you answers in seconds, and then you just have to demonstrate in the field that it can work. A lot of this information, but you can search them on the internet, so I'm not going to spend a whole lot of time. I'm going to spend maybe a minute talking about my institute. It's called Western Transportation Institute. We have 30 people on a full-time basis. We do a lot of research. I'm not going to read the whole thing, but please, if you're interested about Western transportation research or rural transportation, come to our website. We are very well known for road ecology, animals. People heard of Yellowstone National Park and Grand Teton National Park and Glacier National Park. They are all very close by in Montana. We have three biggest, the most beautiful national parks in the world. Is within reach. Going to Yellowstone is an hour drive. Grand Teton is 2 hours. And Glacier National is about 4 or 5 hours. But the biggest challenge regarding transportation are animals, wild animals, the collisions they cause, okay? It's a very serious problem. So we do a lot of research in this area. Of course, I talk about payment evaluation. This has been my work and passion in the last 3 decades. I'm hoping spending another decade on this, and then that will wrap up my career, maybe. This is the latest one. It's a 3D laser imaging. We're having the world's highest resolution, 0.5 millimeter, complete coverage, full lane at highway speed, 60 miles an hour or roughly 100 kilometers an hour. Our next competition is 1 millimeter, so about half our resolution. So this is the data quality we can get. About 10 years ago, I told my team, about 10 people, half staff, half PhD students, I said, everybody, I kind of immersed myself into this about a year. Now it's ready to do it. So 2015, we had a meeting. I said, if you guys had a topic that's not on deep learning, change it. So everybody changed to deep learning 10 years ago. We were the first to do this for payment evaluation. Right now, we have a working system in the field, deployed in Japan, in China, in South Africa, in Brazil, and of course in the US. US Army Corps of Engineers has a system from us to do that. So, one thing I need to talk about before I conclude my presentation would be safety sensor. I mentioned 4 categories of payment evaluation, right? One of them is mature, which is longitudinal profiling. People have been working on this for the last 3 or 4 decades. Finally, we have a good solution today, zero speed. You can stop and go and still get accurate data. But for payment friction testing, payment texture measurement, we were stuck. Some of you are familiar with current ASTM and AASHTO standards on payment friction testing, which is based on what Newton told us 300 or 400 years ago. So you place a weight on a pavement, or in this case, if in physics, you place a weight on the surface, and then you drag the weight. The relationship between the weight and dragging force is the friction. Right? We learned that in high school. That's what we use today. This beautiful, simple philosophy or concept does not work well on pavement just because you have to put water on the pavement surface, for one. You have to use the ASTM standard tire, which wears out in 300 miles. So the new tire and then 300-mile tire would give you different numbers. And the water cannot be perfectly controlled. And the temperature would cause problems of the tire pressure in the morning and in the afternoon. All those factors are not controllable. So what do you get? You get data that's not consistent, that's not repeatable, that can tell you real bad payments and very good payments, but anything in between is a guess. Okay, so what's the solution? about roughly 5-6 years ago, we said we're going to do a laser imaging so that we can capture the data consistently and accurately at 0.1 millimeter level. We know that 0.5 millimeter is the macro texture, and 0.1 millimeter covers a large portion of the micro texture. So we have both micro texture and macro texture captured at highway speed, and it's easy said than done, just because you cannot really driving at 1 kilometers an hour. You need to drive at highway speed. And this is the data we demonstrated about 5-6 years ago at 0.1 millimeter resolution. With this kind of surface information, which is the same every time you collect it, as long as the pavement is dry, we don't need water, dry pavement, that's all you need. It's highly repeatable, it's the same surface, which means our base data is there to represent a virtual surface. And then we can interpret the surface for texture data, for friction data. Now, this is another shot that we achieved roughly 5-6 years ago. Of course, this type of quality data was collected at very, very slow speed. The reason being is at highway speed, we have a physics limitation. We roughly can get 30,000 pictures of the pavement a second, but we need to have at least 10 times faster speed to get the same quality of data at highway speed. So that tells us that we need to do something about it. So we actually use AI to improve the pavement resolution in the longitudinal direction by learning. What do I mean by learning? So we drive the vehicle very slow to capture the pavement quality at something that's shown on the screen. And then we also drive it at very fast, same pavement. Then we tell the AI, hey, dude, this is the same pavement, okay? The data from the high speed, data from the low speed, same pavement, but the low speed is the real one. Can you regenerate for me in future payments? So this is also a very simple concept. Deep learning is very good at that. So we actually produced several models how to regenerate pavement surface by a factor of 10 to 100 times resolution, okay? So this just give you an example. For the truth is on the right, and then 4 times data restored is on the upper left. It's very close, it's not identical, but we are still in the preliminary stage of using AI to restore or reconstruct pavement surface. If the common term, the technical term is called super resolution. So Microsoft, Amazon, they have hundreds of people working on super resolution, okay, today, to restore or reconstruct visual information. So we use it to do one directional improvement, which is, can be more powerful in some ways. And we're able to do a highly correlated data for MPD and MTD for macro texture, and also for microtexture, we use wavelength energy to simulate, and it has demonstrated highly correlated data. So what this initial research tells us is we should be able to use the safety sensor through a non-contact way to reconstruct a virtual surface to do texture and safety and friction analysis. So this one just finished a few months ago in the summer in Montana for WTI. Using the technology we accumulated or we developed in the last 3 decades. This is the latest generation. The one on the right side is the safety sensor. It's hanging relatively low, about ½ meter from the surface of pavement. We use a visible blue laser light to capture the micro and the macro texture information. So as promised, I think I did my presentation in less than 30 minutes. Yeah, for the young people in this audience, we have a few of you here. If you do not use AI, you lose a competitive edge in your career, okay? Because everybody will be using it. It's getting more powerful. But there is a talk in the community about AI is hitting a wall. So last 10 years, it went up real fast from ChatGPT 1, 2, 3, 4, and from 4 to 5 is a marginal improvement. It's actually slower. And then, so can OpenAI and other companies to restart the AI research, so it's going to climb again exponentially? We don't know that. If we really hitting a wall, it's like marginal improvements, 1 or 2% every year, then we got stuck, right? Just to let you guys know, the so-called deep learning is nothing more, is a huge neural net. It's based on a hunch many decades ago that neuroscientists and mathematicians, they think that we can model humans' neurons by using artificial neurons in a computer. Okay, so that concept is the same. It didn't change at all, but they, of course, did a lot of customization. It's nothing more of using extraordinary big matrices, billions and billions of elements. Most of the elements are zeros, but the ones are not zeros would play a critical role. So they do not have computation with those matrices with billions and billions of elements. In the initial customization called the CNN, right now they have different ways of doing it. But the bottom line is still binary digital based. It's still traditional computer based. It's mostly GPU based, but it is a computation of large matrices. And they do that real fast. And most of the cases, they give us good answers today. But anyhow, we have a lot of challenges in front of us. Power consumption is one. People are looking at doing small nuclear reactors to power, the AI data centers in the next few years. We do have ethics and education issues to face. Our next generation, the young kids today, in 5 or 10 years, what do they learn in school? Because their knowledge is all over them. They don't have to study anymore. So what's going to happen to the next generation? And it's a huge problem for us, I guess. Anyhow, Camille, I finished my presentation, so I can take any questions.
Thank you very much. So we are really back on track here. So we have some time for a few questions.
Can you hear me okay?
I'm going to turn it on.
On or off?
There you go. No, yeah.
People can hear me? Can you hear me back there? First of all, I reinforce the idea that Kelvin is really in the genius level, in my opinion. Brilliant guy. And it's going to take a lot of brilliance to do all the things that you're talking about. What I've noted, and I dealt with a lot of big databases in my life, are a few things. First, you can have bad data. So what is truth? And you're trying to, you have truth, and then you're going to magnify it 128 times or whatever. But if you magnify something that's wrong 128 times, it's still wrong. So maybe you might spend a little time on how does one specify truth for these models to know this is the truth. The fear is AI will begin to generate its own truth, and then we're all messed up. So perhaps you could spend, have a little time, a little deep thought. Nowadays, AI says, when you go to it, has all this stuff, and then it says, if you want to do some deep thinking, well, most people don't do that. But in your case, you do. And I'd like to hear your comments on that.
Right. Today's AI for practical applications, in most cases, they are very crude. So George made a very good comment. I didn't dive into it just because of lack of time. For example, when we increase the longitudinal resolution by a factor of 10 or even 100, how do you know the regenerated data is good enough? What we did is we did statistical comparisons. So we literally collected data on dozens of sites at high speed, low speed, and some of the high speed, low speed data was used in training. The other one was used to verify that actually the result is correct. And we have to do that exercise. And actually, in most applications, you have to verify to generate the so-called the precision and bias information. That's a traditional statistical method. We cannot get away from that yet. We don't have enough confidence, actually, in the AI system today. But the good news is, just in last 2 or 3 years, large companies on a worldwide basis, most US-based, some in Europe, some in China, they're developing platforms that you can use, especially those open source platforms. You can use them and convert them into your own, doing customization. My team is doing that today. We didn't do that 10 years ago. 10 years ago, we developed our own so-called brain. It's a small brain just for cracking analysis. It worked well. Let me tell you a story why the traditional imaging failed in payment evaluation for years and years. Well, I know we have a little bit of time, but roughly 20 years ago, there's a company called L'Oreal, which was bought by General Dynamics or something. They actually developed vision systems for fighter jets, like F-15 and F-16 type. So when those guys found out there's a federal highway has a huge problem about finding cracks, they said, heck, when our fighter jets take off, within seconds, they know what's in the sky, 500 miles away, what type of aircraft in there. They use vision systems. They said, we do that in 5 seconds. But your cracking is so it's like a baby problem. So the Federal Highway gave them like a $250,000, just like 20 years ago. They said, DOD asked us to write proposals for $5 million a piece, just writing the proposals. You give us $250,000 to resolve the problem, but this problem is so simple. They spent 2 years to finish the $250,000. They didn't do anything. The problem is just it's very difficult. For those people here, if you are not involved in payment analysis, you think finding cracks is easy. It is easy for a child. A child can learn this is a crack. The child would not make a mistake. Why is that? Why you have 10 PhDs working for 10 years? You build a math model. That model can work on 5 miles perfectly. And next 5 miles, it fails. It fails. And then the third 5 miles, it worked moderately well. And then the fourth 5 miles, it failed again. So the statistical traditional math methods never worked in our domain for payment surface evaluation. So AI can work just because it has the cognition capability like a child. Okay, it's not identical, it's not the same, but it does have that property in there. But it's getting better, right? So, OpenAI, Microsoft, Amazon, Google, and some companies in Europe and China, they're spending billions every year to build platforms to mimic human brain. Right now, it's like getting the knowledge, getting trained, and then how to do inferencing, and then hopefully in 5-10 years, how to do innovations. So that's the key. When AI can do innovations, I think research universities in the world are in huge trouble. Just because those innovations can be done in a fraction of a second instead of years. A PhD takes 4 years right now. I mean, those innovations by those AI engines, they can essentially tell them a problem, describe the problem. Describing the problem takes more time, but for them to give an answer in a second, and the answer is good, and it's better than a PhD thesis, it's coming to us. Hopefully, in my lifetime, that's very dangerous for a lot of things. So, anyhow, I don't want to take too much time, but we're in an interesting era. I'm glad, we have material scientists here. Ask Robert, solving a huge waste problem for the environment while improving the performance of our payments. This is great. I think, next, I believe 3 years later, we're going to have another conference. Hopefully, more people are talking about AI, how to use them in Ask Robert.
Question?
Thank you.
Any other questions? Well, thank you, Professor Calvin, on this great insight on AI and payment engineering. Appreciate your talk to that. There's a question there. Okay, well, go ahead, Mona. If you don't mind coming up here, yes.
Hi, everyone.
Yeah, you just get closer to it.
Hi, everyone. My name is Mona Noor Al Huda, and I had the honor and pleasure working for both Georges. And my question today is the authenticity of the AI information, how you verify it, or how it's going to be verified. Because as I noticed, or I worked with AI, normally, if you didn't give the whole, everything in the step, and still you are not going to get the right information from it. So I'm just wondering, and it's a very great presentation anyway.
Thank you. For engineering problem solving, the verification for us is through traditional methods. Okay, statistical methods. We have to collect the data, do the analysis, figure out and know the truth, but put the truth aside and then compare. I believe most scientists or engineers today, they still do that. AI makes mistakes. AI sometimes does hallucination. You guys know what hallucination is? It gives you data with confidence, but it's completely wrong. Like sometimes you ask ChatGPT a question, most of the time you would give the correct answer, sometimes it gives you a wrong answer. It's so wrong that you said, why are you making a mistake like this? And it's going to apologize, but the way it presents the answer is like, I'm the God, I know it. So in those cases, you just have to be guarded, right? You cannot take the answers as truth. Yes, but in engineering, I think we have to use traditional methods to verify. I believe those large platforms, large companies actually are developing technologies to verify if the answer from AI is wrong or correct by another AI, okay? So all those things are coming along eventually. Yeah, but those are challenges for sure, yes.
Thank you so much.
Yes, thank you.
My AI is better than your AI.
It's amazing how many people from the state of Arizona represented in this conference. We love Portugal, I guess. It's a great, I feel like we took over the conference here at some point. Well, thank you again, Calvin. Really great talk. Big round of applause for Professor Calvin.
Thank you.
And George, are there any announcements before lunchtime here? Nope, we are good. So lunch is served in the same place, in the hot house? Yep. All right. Enjoy lunch. We'll see you afternoon.
Very fine job. Thank you so much. It's a tough subject, I know.